Welcome back to Sleepy Tinfoil Hat. Settle into wherever you are tonight. Let your shoulders drop. Let your breath find its slower rhythm. Because we are going to spend the next several hours walking together through one of the most familiar, yet most genuinely strange features of the planet we live on. Mountains. They sit on the horizon of every continent we have ever inhabited. They have shaped the climates and cultures and migration patterns of our species for as long as our species has existed. They are so common in our experience that we tend to take them for granted, as if they were simply part of the natural backdrop of existence. But mountains, when you actually start examining them carefully, turn out to be far stranger and more interesting than the casual encounter suggests. And the questions they raise touch some of the deepest mysteries of geology, climate, biology, and human cultural history. Before we go further, I want to ask a small favor. If you find this kind of slow, careful exploration helpful for falling asleep, or if some part of your mind genuinely enjoys thinking about the deep features of the world while the rest of you drifts toward unconsciousness, please consider subscribing to Sleepy Tinfoil Hat. The channel grows when listeners signal that they are here, and the algorithm is the only way new people find their way to this kind of patient nighttime thinking. And if you would, leave a quiet note in the comments telling me where in the world you are tonight. The country, the city, the hour on your clock if you want to share it. I read these. There is something genuinely moving about watching the slowly forming map of where this audience is scattered, all of us awake or trying not to be at the same hour, listening to the same voice across many different time zones and many different lives. So tell me where you are and then settle deeper, because the journey from here will be long and patient and, I think, worth taking carefully. Now let me begin where most discussions of mountains begin, which is with the basic question of what a mountain actually is. The intuitive answer is straightforward. A mountain is a large landform that rises significantly above the surrounding terrain, with steep slopes and often a peak or summit at its highest point. This intuitive definition works well enough for casual purposes, but when you try to make it precise, you run into difficulties almost immediately. How much height is required for a landform to count as a mountain rather than a hill? The answer turns out to vary enormously across different traditions and definitions. In the United Kingdom, a traditional definition holds that a mountain must rise at least 600 meters above the surrounding terrain, though this threshold has been revised multiple times. In the United States, the Geographic Names Information System has used different cutoffs in different periods, sometimes setting the threshold at 300 meters above the surrounding terrain. In some alpine regions, even smaller landforms are commonly called mountains because they have particular cultural or historical significance. The category of mountain, in other words, is partly defined by physical characteristics and partly defined by cultural conventions, and the boundaries of the category are fuzzy. This may seem like a trivial point about definitions, but it points to something more interesting. Mountains are not a single uniform phenomenon that we can easily categorize and analyze. They are a diverse set of landforms produced by a variety of different geological processes, occurring in different contexts across the planet, with different histories and different fates. The Andes are not the same kind of feature as the Appalachians, even though we use the same word for both. The Himalayas are not the same kind of feature as the volcanic peaks of the Hawaiian Islands, even though we apply the term mountain to all of them. The diversity of what we call mountains, when you actually examine the various examples carefully, is remarkable, and the geological stories behind the various mountain ranges are genuinely strange when you understand them properly. Let me start with the most fundamental fact about how mountains form, because this fact is itself genuinely strange and was not understood by science until relatively recently. Mountains, in most cases, are produced by the slow movement of enormous slabs of the Earth's surface, called tectonic plates, that float on the partially molten rock of the planet's mantle below. These plates are constantly moving, at speeds comparable to the rate at which fingernails grow, in patterns that have been carefully mapped by geologists over the past several decades. When two plates collide with each other, the resulting compression can produce mountain ranges as the rock on the surface is forced upward. When two plates pull apart, the resulting tension can produce different kinds of mountain formations as material rises from below. When one plate slides beneath another in a process called subduction, the resulting interactions can produce volcanic mountain chains along the boundary. The major mountain ranges of the world are mostly products of these tectonic interactions, and the specific characteristics of each range reflect the specific geological history of how the relevant plates have been moving. This understanding of mountain formation is relatively new. The theory of plate tectonics, which provides the framework for understanding how mountains form, was not widely accepted until the 1960s, just a few decades ago. Before that, the origins of mountain ranges were genuinely puzzling to geologists, with various theories being proposed and debated without any decisive resolution. The German meteorologist Alfred Wegener proposed something like the modern theory in the early 20th century, but his ideas were rejected by most geologists for decades. The eventual acceptance of plate tectonics came only with the accumulation of multiple lines of evidence, including the mapping of the seafloor, the discovery of seafloor spreading, the analysis of magnetic patterns in oceanic rocks, and the precise measurement of plate movements using modern techniques. The understanding that we now have of how mountains form is therefore quite recent in scientific history, and it represents a genuine revolution in how we think about the planet's surface. The implications of plate tectonics for how we should think about mountains are substantial. Mountains are not static features. They are dynamic structures that are constantly being built up by tectonic forces and worn down by erosion. The visible mountain ranges of the world are the current state of an ongoing process, with new mountains being formed in some regions and old mountains being eroded into nothing in other regions. The Himalayas, for instance, are currently rising at a rate of about 5 millimeters per year, as the Indian tectonic plate continues to push northward into the Eurasian plate. This may seem like a slow rate, but over geological timescales, it adds up. The Himalayas have been growing for approximately 50 million years, and they continue to grow today. They are still in the process of being formed, even as they appear to us as stable and permanent features of the landscape. At the same time, the mountains we see are also constantly being eroded. Wind, water, ice, and gravity all act to wear down mountain surfaces, carrying material away from the peaks and depositing it in valleys, plains, and ultimately in the oceans. The Appalachian Mountains in eastern North America were once much taller than they are today, possibly comparable in height to the modern Himalayas. But hundreds of millions of years of erosion have worn them down to their current relatively modest profile. Every mountain range is therefore in a balance between the forces that build it up and the forces that wear it down, and the visible features we see represent the current state of this ongoing balance. I want to draw your attention to something genuinely strange about this. The mountains that surround us, the ranges we can see on the horizon, and that figure in our cultural and literary traditions are not permanent features of the planet. They are temporary structures, in geological terms, that have specific histories and that will eventually disappear as erosion wears them away. The mountains we see today are not the mountains that were here 100 million years ago, and they are not the mountains that will be here 100 million years from now. The landscape of the planet is constantly changing, with mountains rising and falling across geological timescales in ways that we cannot easily perceive because the changes are so slow. We tend to think of mountains as essentially eternal features, but they are anything but eternal. They are some of the most dynamic structures on the planet's surface, constantly in motion, constantly being remade. This changes how we should think about the relationship between mountains and the cultures that have lived among them. Human civilization is approximately 10,000 years old in its agricultural form, and our species has existed for perhaps 300,000 years. These are short periods compared to the timescales over which mountains form and erode. The mountains that have shaped human cultures, that have figured in human mythology and religion and history, have been essentially the same mountains throughout the entire span of human existence. We have lived with mountains that have not changed perceptibly during our species' lifetime, even though the mountains are themselves in motion at scales we cannot perceive. The relationship between humans and mountains has therefore been a relationship between very short-lived creatures and very long-lived but ultimately impermanent features of the landscape. What I want to do tonight, across the parts that follow, is take you slowly through the various aspects of mountains that I find genuinely interesting. We will look at how specific mountain ranges formed, including the dramatic stories of the Himalayas, the Andes, the Alps, and other major ranges. We will examine the strange biology of high altitudes, including how plants and animals and humans have adapted to thin air and cold temperatures. We will consider the role of mountains in shaping climate and weather patterns, with the rain shadows and wind patterns and snow accumulation that mountains produce. We will look at the cultural significance of mountains across various human traditions, including the religious and spiritual associations that mountains have held in nearly every human culture that has lived among them. We will think about the strange ecosystems that exist on mountainsides, with their distinctive plants and animals adapted to the specific conditions of high terrain. And we will consider some of the genuinely puzzling features of mountains that do not fit neatly into any standard explanation. What I am not going to do is provide you with simple romantic descriptions of mountain scenery, though there will be some of that woven through the technical material. The popular treatment of mountains tends to emphasize their visual beauty and their inspirational qualities, and these are real and worth acknowledging. But the deeper interest of mountains lies in what they actually are, how they came to be, what they do to the climate and the biology around them, and how they have shaped human existence throughout the long course of our species' history. The careful examination of these aspects is, I think, far more interesting than mere appreciation of mountain scenery, and it is the kind of careful examination that suits a long, quiet night spent in slow contemplation. The thing I want you to hold in your mind as we settle into this exploration is that you live on a planet whose surface is constantly being shaped by enormous forces operating at timescales far longer than human existence. The mountains you can see, if you live within view of any mountains, are products of these forces, currently in their visible form, but participating in larger processes that will continue long after you are gone. You are a brief observer of features that have specific histories extending back millions of years and futures extending forward similarly long. The careful contemplation of such features, on a quiet night like this one, is one of the small ways that we can briefly touch the deep timescales that the planet operates on, far below the rapid rhythms of human concern. Lower the lights, if you have not already. Let your awareness soften. The mountains we are about to discuss have stood through countless nights longer than the night you are spending now. They have witnessed, in their geological way, the rise and fall of multiple human civilizations. They have endured ice ages and warm periods, floods and droughts, the comings and goings of countless species. They will continue to stand, in some form, through countless more nights after both of us are gone. We're about to spend a long, quiet evening with features that operate on timescales vastly longer than our own, and the contemplation of them is itself a kind of communion with the deep history of the planet that produced us. Tonight, I want to take you to perhaps the most spectacular ongoing geological event on the planet, an event that has been unfolding for tens of millions of years. Tonight, I want to take you to perhaps the most spectacular ongoing geological event on the planet, an event that has been unfolding for tens of millions of years and that continues to unfold beneath our feet at this very moment. I am talking about the formation of the Himalayas, the highest mountain range on Earth, and the story of how this range came to be is one of the most genuinely dramatic narratives in all of geology. It is a story of continental collision on a scale that is difficult to imagine, of rocks being lifted from sea floors to elevations far above the clouds, and of forces that continue to reshape an entire region of the planet in ways that will continue for millions of years to come. Let me set the scene by going back to a time long before there were any humans on Earth. Indeed, long before there were any mammals of significant size. About 170 million years ago, during the period that geologists call the Jurassic, the surface of the Earth was arranged very differently than it is today. The continents were configured in patterns we would not recognize, with what is now the Indian subcontinent existing as a separate landmass, located far to the south of where it is today, somewhere in the southern hemisphere near what is now Antarctica. India was an island surrounded by ancient oceans, drifting on the slow currents of the planet's tectonic system in patterns that would not be obvious to anyone observing them at the time. The drift was so slow that no individual creature would have noticed any change during its lifetime. But the drift continued, generation after generation of plants and animals living on this island continent, with the position of India gradually shifting over the course of millions of years. About 140 million years ago, India began to move northward at what was, by geological standards, a remarkable speed. The Indian plate accelerated to a velocity of approximately 15 centimeters per year, relative to the Eurasian plate to the north. This may sound slow, and on human timescales it is, but in geological terms, it is genuinely fast, several times faster than most plate movements that occur on Earth. India became, in essence, a runaway continent, drifting northward across what was then a vast ocean called the Tethys Sea, heading toward an eventual collision with the Eurasian plate. The journey took tens of millions of years, with India crossing thousands of kilometers of ocean as it moved. During this period, the climate, biology, and ecology of the Indian subcontinent developed in isolation from the rest of the world, producing distinctive flora and fauna that would eventually be brought into contact with the Eurasian biotic communities when the two land masses finally met. The collision began approximately 50 million years ago, when the leading edge of the Indian plate first made contact with the southern margin of the Eurasian plate. The initial encounter was geological rather than dramatic, with the two plates meeting at the seafloor of the Tethys Sea, which gradually closed as India continued to push northward. The seafloor sediments that had accumulated over millions of years on the bed of the Tethys, along with the marine rocks and the remains of countless marine organisms, were caught between the two converging plates. As the collision progressed, these marine materials were forced upward, scraped off the descending Indian plate as it pushed beneath the Eurasian plate, and stacked into thick sequences that would eventually form the foundations of the Himalayas. The rocks at the top of Mount Everest, the highest point on Earth, are marine limestones containing fossilized sea creatures, lifted from what was once the floor of the Tethys Sea to elevations of nearly 9,000 meters above modern sea level. The rocks have not changed. They are still the same marine sediments that they were when they formed at the bottom of an ancient ocean. What has changed is their position. They have been carried by the inexorable force of the continental collision, from the depths of the sea to the heights of the world. This is, I want to emphasize, a genuinely strange thing to contemplate. The summit of Everest, which mountaineers approach with such effort and reverence, consists of fossiliferous limestone that originally formed underwater. The shells and skeletons of ancient marine organisms are preserved in the rock at the highest point on the planet, having been carried there over the course of 50 million years of continuous tectonic activity. If you could climb to the top of Everest and examine the rocks carefully, you would find evidence of the marine origin of the material embedded in the very stone of the summit. The mountain that humans regard as the embodiment of high terrestrial elevation is, at its peak, made of material that was once the bottom of the sea. The history of the planet has, in this case, achieved a complete inversion, with the lowest place on the ancient Earth becoming the highest place on the modern Earth, and the inversion took 50 million years to accomplish. The collision between India and Eurasia did not stop when the two plates first made contact. India has continued to push northward at a slower but still substantial rate ever since the initial collision began. The current rate of movement is approximately 5 centimeters per year, slowed from the original speed, but still significant. This continued northward push has several consequences that shape the modern Himalayan region. First, the mountains continue to rise as the compression between the two plates forces the rock at the surface upward. The Himalayas are, on average, getting taller by about 5 millimeters per year, though the rate varies in different parts of the range. Second, the entire Tibetan Plateau to the north of the Himalayas is being uplifted, with the high terrain of Central Asia being maintained by the ongoing pressure from the Indian collision. Third, the region is one of the most seismically active on Earth, with frequent earthquakes resulting from the continuing tectonic interactions. The major earthquake that devastated Nepal in 2015, killing thousands of people and reshaping portions of the Himalayan landscape, was a direct expression of the same forces that have been building the mountains for the past 50 million years. Fourth, the geography of the entire region continues to evolve, with rivers shifting their courses, valleys deepening, and the precise patterns of erosion responding to the ongoing changes in elevation. The biological consequences of the Himalayas are equally striking. The rise of these mountains has fundamentally reshaped the climate of much of Asia. The Himalayan range acts as an enormous barrier to atmospheric circulation, blocking the northward movement of moisture from the Indian Ocean during the summer monsoon season. The moisture that would otherwise have spread across Central Asia is instead forced upward by the mountain barrier, where it cools, condenses, and falls as the heavy monsoon rains that drench the southern slopes of the Himalayas and the Indian subcontinent. North of the mountains, the air that descends after crossing the range has lost most of its moisture, producing the relatively dry conditions of the Tibetan Plateau and the deserts of Central Asia. The entire climate of Southern Asia, with its monsoon-driven agricultural systems supporting billions of people, depends on the existence of the Himalayan barrier. Without these mountains, the climate of the entire region would be completely different, and human history would have unfolded in radically different ways. The cultural significance of the Himalayas, both for the peoples who have lived among them and for distant cultures that have known of them through trade and travel, is profound. The mountains have been understood as sacred in nearly every cultural tradition that has encountered them. In Hindu cosmology, Mount Meru, the cosmic mountain at the center of the universe, has been associated with various peaks in the Himalayan region, with different traditions identifying different specific mountains as the sacred Meru. In Tibetan Buddhism, particular mountains have been recognized as homes of specific deities and as sites where the boundaries between ordinary reality and other dimensions of existence are particularly thin. In the Bon religion that preceded Buddhism in Tibet, mountains were similarly understood as sacred presences with their own consciousness and agency. The general pattern across these traditions is that the Himalayas have been experienced not just as impressive physical features, but as living presences with religious and cosmological significance. The peoples who have lived in the shadow of these mountains for thousands of years have developed elaborate frameworks for understanding their relationship with the mountains, frameworks that treat the mountains as participants in cosmic order, rather than as merely physical objects. I want to address something that I think is genuinely interesting about the human experience of the Himalayas. The peoples who have lived at high altitudes in the Himalayan region, including the Tibetans, the Sherpas, and various other groups, have developed biological adaptations to the thin air and harsh conditions of high elevation. The Tibetan adaptation to altitude is particularly remarkable, involving genetic variants that affect oxygen utilization, blood characteristics, and cardiovascular function. We touched on the Denisovan origin of certain Tibetan altitude adaptations earlier in this exploration, but the broader picture is worth noting here. The peoples of the high Himalayas are not just culturally adapted to mountain life, they are biologically adapted in ways that distinguish them from lowland populations, and the adaptations took thousands of years to develop. The relationship between these populations and the mountains has therefore been not just cultural, but genetic, with the mountains literally shaping the bodies of the people who have lived among them for many generations. The peaks of the Himalayas have held a particular fascination for humans across many cultures. The highest peaks, including Everest, K2, Kanchenjunga, and others, have been objects of mountaineering aspiration for the past century and a half. The history of attempts to climb these peaks is itself a remarkable story, involving extraordinary feats of human endurance and courage, along with substantial loss of life. The first successful ascent of Everest by Edmund Hillary and Tenzing Norgay in 1953 was widely understood as a major achievement in the human relationship with the planet. The continued attempts to climb the major Himalayan peaks, with the various successes and disasters that have accompanied them, reflect a particular kind of human engagement with extreme environments that probably has deep roots in our species' history of exploration and challenge. But I want to point out something that may not be immediately obvious about the relationship between humans and Himalayan peaks. The peoples who have lived in the shadow of these mountains for centuries did not generally climb them. The traditional cultures of the region recognized the peaks as sacred, and ascending them was understood as inappropriate or even sacrilegious. The ascent of Everest by Hillary and Tenzing was a culmination of efforts by Western mountaineers, and it was undertaken in a framework that treated the climbing of mountains as a worthwhile achievement in its own right. The traditional Tibetan and Nepalese cultures had different orientations toward the mountains, treating them as sacred presences that deserved respect and reverence rather than as objectives to be conquered. The modern phenomenon of mountaineering, with its emphasis on summiting peaks for the achievement itself, represents a relatively recent and culturally specific approach to mountains that is different from how mountains have been understood across most of human history. There is one more aspect of the Himalayan story I want to bring in before we close this part. The fact that India is still moving northward, still pushing into Eurasia, means that the Himalayas are not finished forming. They will continue to rise for many more millions of years, eventually reaching elevations and configurations that we cannot fully predict. The continued tectonic activity will continue to produce earthquakes, will continue to reshape the geography of the region, and will continue to influence the climate and biology of Southern Asia. The Himalayas that we see today are a snapshot of an ongoing geological process, and the mountains that future generations of humans will see, if humans continue to exist for the relevant timescales, will be different from the mountains we see now. They may be higher in some areas, as continued uplift outpaces erosion. They may be lower in other areas, as erosion catches up with uplift. The precise patterns will depend on the specific interactions between tectonic forces and erosional processes, but the larger pattern of continued change is essentially certain. So as you continue to drift, hold this image in your mind. A peak in the Himalayas, perhaps Everest itself, standing at its current elevation in the dark. The wind howls around the summit. The cold is intense beyond what most humans can experience without protection. The rocks of the summit, those marine limestones lifted from the floor of an ancient sea, stand silently in the night. They have been there in roughly their current position for some thousands of years, and they will be there in roughly their current position for thousands more, even as the larger geological process continues to push them gradually upward. Far below, in the valleys at the base of the mountains, communities of humans are also asleep in the same darkness that surrounds the summit. The mountains and the people exist together on radically different timescales, with the people coming and going across human generations, while the mountains continue their slow geological work. The relationship has been the relationship for as long as humans have lived in this region, with each generation of humans encountering the same essentially unchanged mountains, while the mountains continue their slow change in ways that no individual human has ever lived long enough to perceive directly. Tonight, like every night, the mountains stand. Tonight, like every night, the people sleep. The continuity is real, even across the enormous differences of timescale that separate the two kinds of existence. Tonight I want to take you to a different kind of mountain, formed by a different kind of geological process, with a different kind of history and a different kind of significance. I want to take you to the Andes, the longest continental mountain range on Earth, stretching for nearly 7,000 kilometers along the western edge of South America. The Andes are not the highest mountains on the planet, though they include some of the highest peaks outside Asia. What makes them remarkable is their length, their continuity, their geological complexity, and the role they have played in shaping both the climate of an entire continent and the cultural development of the human civilizations that have lived among them for thousands of years. Let me start with how the Andes formed, because the story is genuinely different from the story of the Himalayas. While the Himalayas were produced by the collision of two continental plates, the Andes were produced by a different kind of tectonic interaction called subduction. Along the western edge of South America, the oceanic plate of the Pacific Ocean is being slowly forced beneath the continental plate of South America. This subduction process has been occurring for tens of millions of years and continues today. As the oceanic plate descends into the Earth's mantle, several things happen at the boundary. First, the descending plate carries water and other materials down with it, where the heat and pressure cause the materials to melt and produce magma that rises through the overlying continental crust. This magma, when it reaches the surface, produces the volcanic activity that has built much of the Andes. Second, The compression of the continental plate by the descending oceanic plate causes the surface rocks to be folded and faulted, producing the mountain structures we now see. Third, the entire western edge of the South American continent is being slowly lifted by the ongoing tectonic interaction, with the Andes representing the elevated zone of this uplift. The volcanic component of the Andes is particularly significant. The range includes more than 200 volcanoes, many of which are still active, distributed along its length in patterns that reflect the underlying subduction geometry. Some of these volcanoes are among the highest in the world, including Ojos del Salado on the Chile-Argentina border, which at nearly 7,000 meters is the highest active volcano on Earth. The volcanic activity has produced not only the obvious volcanic peaks, but also vast volcanic fields, ash deposits, and various other features that shape the landscape. The volcanic component distinguishes the Andes from the Himalayas in important ways. The Himalayas are essentially non-volcanic, since they were produced by continental collision rather than by subduction. The Andes are extensively volcanic, with the volcanic activity continuing to be a major factor in the geological evolution of the range. The implications of the Andean geology for the surrounding environment are substantial. The volcanic activity contributes various materials to the soils and waters of the region, with effects on agriculture, mineral resources, and biological diversity. The mountains produce a strong rain shadow effect on the western coast of South America, with the Atacama Desert in northern Chile being one of the driest places on Earth specifically, because the Andes block the moisture coming from the Atlantic Ocean to the east. The eastern slopes of the Andes, by contrast, receive substantial rainfall as moisture from the Amazon basin rises against the mountain barrier and precipitates. The dramatic climate gradient across the Andes, from the arid coast on the west to the humid Amazonian foothills on the east, has produced an extraordinary diversity of ecosystems, ranging from coastal deserts to high Andean grasslands to tropical rainforests, all within relatively short horizontal distances. The biological diversity of the Andean region is among the highest on the planet, partly because of this dramatic climate variation across the range. I want to take you now to the human cultures that developed in and around the Andes, because the relationship between Andean civilizations and their mountain environment is one of the most striking examples of how humans have adapted to specific geographic conditions. The Andes have supported continuous human occupation for at least 14,000 years, with archaeological evidence of human presence going back to the very end of the Pleistocene. The peoples who developed in the Andean region created some of the most sophisticated civilizations in pre-Columbian America, including the Chavin, the Moche, the Tiwanaku, the Wari, and most famously the Inca, whose empire dominated much of South America in the centuries before the Spanish conquest. Each of these civilizations developed distinctive adaptations to the mountain environment, with the Inca representing the culmination of a long tradition of high-altitude civilization that has few parallels anywhere else in the world. The Inca Empire, at its peak in the early 16th century, controlled territory extending from modern Colombia to central Chile, with a population estimated at around 10 million people. The empire was unified by an extraordinary system of roads called the Capacñan that extended for more than 30,000 kilometers through some of the most rugged terrain in the world. These roads crossed mountain passes at elevations over 4,000 meters, included suspension bridges across deep canyons, and connected the various provinces of the empire with a network of communication that allowed messages to travel from one end to the other in a matter of days. The roads were maintained by relay runners stationed at intervals, who could carry messages with remarkable speed despite the difficult terrain. The whole infrastructure represents a remarkable adaptation of human engineering to the specific challenges of mountain geography. The agricultural system of the Inca, similarly, was adapted to mountain conditions in ways that allowed substantial populations to thrive at elevations where most agricultural traditions would have failed. The Inca developed extensive terracing systems on the steep mountain slopes, creating flat agricultural surfaces where natural conditions provided only difficult sloping terrain. The terraces were built with sophisticated drainage and irrigation systems that allowed water to be controlled and distributed in ways that maximized agricultural productivity. The Inca cultivated a variety of crops adapted to high elevations, including potatoes, quinoa, and various other plants that thrive in conditions where most other crops would not grow. The genetic diversity of Andean potatoes is itself a remarkable cultural achievement, with thousands of distinct varieties having been developed by Andean farmers over millennia, each adapted to specific elevations, soils, and climate conditions. The Andean agricultural tradition represents one of the most sophisticated examples of human adaptation to mountain environments anywhere in the world. The cultural and religious significance of the mountains for Andean peoples was profound. The high peaks were understood as living beings, called apus in Quechua, with their own personalities, powers, and relationships with the human communities that lived in their shadows. Each major peak had its own associated deity or spirit, and the relationships between human communities and their local apus were maintained through ongoing ritual practices, including offerings, prayers, and various ceremonies marking important seasonal and life transitions. The mountains were not just impressive features of the landscape. They were participants in the spiritual and social order of Andean civilization, with their well-being being understood as connected to the well-being of the human communities. This relationship persists in modified forms in many contemporary Andean communities, where the traditional understanding of mountains as living beings continues to inform daily life and ceremonial practice. I want to draw out something that I find particularly interesting about Andean mountain culture. The high mountains were sites of important religious activity, including the practice of capacocha, an Inca ritual that involved the sacrifice of children at high-altitude shrines. The bodies of these sacrificial victims, preserved by the cold, dry conditions of the high peaks, have been recovered by modern archaeologists in remarkable states of preservation. The most famous example is the Ice Maiden, also known as Juanita, a young woman whose body was discovered on the summit of Mount Amparo in Peru in 1995. Juanita had been ritually sacrificed approximately 500 years ago during the period of the Inca Empire, and her body had been preserved nearly perfectly by the cold conditions of the mountain peak. The discovery of Juanita and other capacocha victims has provided extraordinary information about Inca religious practice, while also raising serious questions about the meaning of these rituals and the nature of the relationship between Andean peoples and their mountain deities. The capacocha ritual, while disturbing to modern sensibilities, was understood by the Inca as a profound act of communication between the human community and the apus of the mountains. The children chosen for sacrifice were honored with elaborate ceremonies before their deaths, and they were understood to be making the ultimate journey to dwell with the mountain gods, where they would advocate for their communities in the spiritual realm. The practice reflected a worldview in which the mountains were genuinely active participants in the lives of human communities, with the relationship between humans and mountains being important enough to merit the most extreme forms of religious commitment. We may judge the practice harshly from our modern perspective, but understanding it requires understanding the Inca worldview within which it made sense, a worldview in which the mountains were living presences, with whom human communities maintained ongoing reciprocal relationships. The fall of the Inca Empire to Spanish conquest in the 16th century was one of the most catastrophic events in the history of the Andean region. The Spanish brought with them not only military conquest, but also diseases that decimated indigenous populations, religious changes that suppressed traditional spiritual practices, and economic systems that disrupted the careful agricultural and infrastructural arrangements that the Inca had developed. The capital city of Cusco was largely destroyed, with Spanish buildings being constructed on top of Inca foundations in many cases. The traditional administrative class was eliminated. The road system fell into disrepair without the central organization that had maintained it. The agricultural terraces were partially abandoned as populations declined and economic priorities shifted. Within a century of the Spanish arrival, the high civilization of the Andes had been dramatically reduced, though substantial elements of Andean culture persisted in modified forms among the surviving indigenous populations. The relationship between the descendants of the Inca and the mountains has continued, however, in transformed but recognizable forms. Modern Andean peoples maintain various traditional practices regarding the Apus and the broader mountain environment. Pilgrimages to sacred peaks continue to be made. Traditional offerings continue to be left at appropriate sites. The agricultural traditions, while modified, continue to draw on the deep knowledge of mountain conditions that Andean farmers have accumulated over millennia. The mountains themselves, of course, have not changed significantly in the 5 centuries since the Spanish conquest. They continue to stand where they have always stood, indifferent to the political and cultural changes that have unfolded around their feet. The Spanish came and went as a colonial power. The modern republics of South America have emerged. The mountains have continued to be the mountains, providing the geographic context within which all these human dramas have played out. There is one more aspect of the Andes I want to bring in before we close this part. The mountains are home to a remarkable array of wildlife, including species that exist nowhere else on Earth. The Andean condor, the largest flying bird in South America, soars over the mountain peaks with a wingspan of more than 3 meters. The vicuña and guanaco, wild relatives of the domesticated llama and alpaca, graze on the high altiplano grasslands. The spectacled bear, the only bear species native to South America, lives in the cloud forests of the Andean foothills. Various species of cats, deer, rodents, and birds occupy specialized ecological niches at different elevations. The biological diversity of the Andean region reflects the diversity of habitats produced by the dramatic climate gradients across the mountains, and it represents one of the most significant concentrations of biodiversity anywhere on the planet. So as you continue to drift, hold this image in your mind. A high Andean valley, perhaps in modern Peru or Bolivia, in the early hours of the morning before dawn. The air is thin and cold. The sky is full of stars, more stars than most modern people ever see. Because the high elevation reduces the atmospheric distortion, and the lack of artificial light pollution at this altitude allows the full majesty of the night sky to be visible. A small village of stone houses sits in the valley, with smoke beginning to rise from a few chimneys as the early risers prepare for the day. The villagers are descendants of peoples who have lived in this valley for hundreds of generations, who have known these specific mountains as their apus, who have maintained their relationships with the high peaks through countless ceremonies and prayers. The mountains rise around the valley, dark against the starlit sky. The same mountains that have stood here through all the changes of history, through the rise and fall of empires, through the comings and goings of countless human generations. The villagers will continue their traditional practices today in modified forms, drawing on the deep cultural inheritance that has been transmitted through their lineages. The mountains will continue to stand in their slow geological way, indifferent to the brief human dramas that unfold beneath them, but participating in the broader cosmic order that the traditional Andean worldview recognizes. The relationship between the people and the mountains is the relationship that it has been for all the centuries that humans have lived here. Tonight, like every night, the connection is being maintained in small ways that no one outside the village will notice, but that contribute to the continuation of one of the longest sustained cultural relationships with mountains anywhere on Earth. Tonight, I want to take you into a category of mountain that exists differently from the others we have been discussing, and that connects mountain processes to some of the most dramatic events on the planet's surface. I want to talk about volcanoes, because volcanic mountains operate on different principles than the tectonic mountains we have examined, and they raise their own distinctive questions about how mountains form, how they affect their surroundings, and what they mean for the communities that live near them. Let me start with the basic mechanics of volcanic mountain formation, because the process is genuinely different from the slow tectonic uplift that produces ranges like the Himalayas. Volcanic mountains form through the accumulation of erupted material at the surface of the Earth. When magma rises from the planet's interior and reaches the surface, it can erupt in various forms, including liquid lava that flows across the landscape, ash, and other particulate matter that falls from the sky after being ejected into the atmosphere, and various other products of volcanic activity. Over time, the accumulated material builds up around the eruption site, eventually forming a mountain. The shape of the resulting volcano depends on the specific characteristics of the eruptions that built it. Volcanoes that produce primarily liquid lava tend to form broad, gently sloping shield volcanoes, with the lava flowing far from the source before cooling and solidifying. Volcanoes that produce thick, viscous lava and substantial amounts of ash tend to form steep-sided stratovolcanoes, with the classic conical shape that most people picture when they think of a volcano. The differences in shape reflect differences in the chemistry of the magma, the gas content, and various other factors that determine how the volcano erupts. The fact that volcanoes can build entire mountains in relatively short periods, geologically speaking, distinguishes them from tectonic mountains in important ways. The Himalayas have been forming for 50 million years and continue to grow at rates of millimeters per year. A volcanic mountain can form much more rapidly, with substantial mountains being built up in periods of thousands or tens of thousands of years rather than millions. Some volcanoes have grown to substantial sizes within human historical memory, with islands rising from the sea or peaks growing dramatically taller during periods of intense volcanic activity. The volcanic mountains of the world include some of the most rapidly formed landforms on the planet, and the speed of their formation gives them a different character than the more slowly built tectonic mountains. Hawaii provides a striking example of volcanic mountain formation. The Hawaiian Islands are a chain of volcanic mountains that have formed over the past several million years as the Pacific tectonic plate has moved over a stationary hotspot in the underlying mantle. The hotspot continuously produces magma, which rises through the moving plate above and erupts at the surface, building volcanic mountains. As the plate moves, the active volcano shifts to a new location, and the previous volcano becomes inactive and gradually erodes. The chain of Hawaiian Islands therefore represents a sequence of volcanoes of progressively increasing age, with the active volcanoes on the Big Island representing the most recent eruption sites, and the older islands to the northwest representing volcanoes that were active in the past but have since become dormant or extinct. The whole island chain is a record of millions of years of volcanic activity, with the geological history of the region being preserved in the sequence of islands that the hotspot has produced. Mauna Loa, on the Big Island of Hawaii, is one of the most massive single mountains on the planet when measured from its true base on the seafloor rather than from sea level. The mountain rises about 4,000 meters above sea level, but its base extends another 5,000 meters below sea level, with the total height from base to summit being approximately 9,000 meters. By this measure, Mauna Loa is comparable in height to Mount Everest, though most of its height is hidden beneath the ocean. The volume of material that makes up Mauna Loa is enormous, far greater than the volume of any single tectonic mountain. The whole island of Hawaii is essentially the upper portion of a vast volcanic edifice that has been built up by millions of years of eruptions, with most of the structure being underwater and only the highest portion being visible as land. Volcanic eruptions produce some of the most dramatic geological events in human historical memory. Mount Vesuvius in Italy erupted in 79 of the Common Era, burying the Roman cities of Pompeii and Herculaneum under meters of ash and debris. The eruption killed thousands of people and preserved the cities beneath the ash, allowing modern archaeologists to recover detailed information about Roman daily life that would otherwise have been lost. The bodies of the victims, preserved as voids in the ash that were later filled with plaster casts, provide haunting images of the moment of destruction, with people captured in poses of fleeing, sheltering, or simply being overwhelmed by the catastrophe. The eruption of Vesuvius is one of the most famous volcanic events in human history, partly because of the elaborate preservation of the victims and the cities, and partly because it occurred in a region with extensive written records that documented the event from the perspective of contemporary observers. The eruption of Krakatoa in 1883 is another example of how dramatically volcanic activity can affect the world. The volcano, located between the islands of Java and Sumatra in modern Indonesia, erupted in a series of massive explosions that destroyed much of the island, generated tsunamis that killed tens of thousands of people in the surrounding region, and ejected enormous quantities of ash and gases into the atmosphere. The explosions were heard at distances of nearly 3,000 miles from the source, with the eruption being audible across portions of 3 continents. The atmospheric effects of the eruption affected weather patterns globally for several years afterward, with cooler temperatures and unusual sunsets being reported across the world as the ejected materials gradually settled out of the atmosphere. The Krakatoa eruption demonstrated how volcanic activity in one region can have effects across the entire planet, with the atmospheric coupling of the global climate system, meaning that major eruptions affect weather and climate everywhere. The eruption of Mount Tambora in 1815, also in modern Indonesia, was even larger than the Krakatoa eruption that followed it 68 years later. The Tambora eruption ejected enormous quantities of material into the upper atmosphere, where the resulting particulate matter blocked sunlight and reduced global temperatures by several degrees. The year following the eruption, 1816, became known as the year without a summer, with crop failures and unusual weather affecting populations across the world. The reduced temperatures led to harvest failures in Europe, North America, and Asia, with associated famines that killed an unknown but substantial number of people. The Tambora eruption is one of the most significant volcanic events in human historical memory in terms of its impact on global climate and human welfare, demonstrating how a single volcanic event can affect the entire planet's atmospheric and ecological systems for years afterward. The relationship between volcanic activity and human civilization has been long and complicated. On one hand, volcanic eruptions have been catastrophic events that have destroyed cities, killed populations, and caused widespread suffering. On the other hand, the volcanic regions of the world have often been particularly attractive for human settlement because of the rich soils that volcanic ash produces. Volcanic soils are often highly fertile, supporting productive agriculture in regions where less fertile soils would limit the populations that could be supported. Many of the most densely populated agricultural regions in the world are located on volcanic soils, including parts of Indonesia, the Philippines, Japan, Central America, and various other regions. The trade-off between the dangers of volcanic activity and the benefits of volcanic soils has been a persistent feature of human settlement patterns in volcanic regions for thousands of years. I want to bring in here something genuinely interesting about how volcanic mountains shape the cultures that live near them. The peoples who have lived in the shadow of active volcanoes have typically developed elaborate cultural frameworks for understanding and responding to the volcanic activity that periodically threatens their communities. In Hawaii, the goddess Pele has been associated with the volcanic activity of the island chain for centuries, with traditions describing her movements among the various volcanoes and the activities that result from her presence. Specific eruptions have been understood in terms of Pele's actions, with the cultural framework providing a way to make sense of events that would otherwise have been incomprehensibly destructive. The Pele tradition is not just a primitive attempt to explain volcanic activity. It is a sophisticated cultural framework that integrates the volcanic phenomena into the broader cosmological understanding of the Hawaiian people, with associated religious practices, taboos, and respectful relationships with the volcanic landscape. Similar cultural frameworks exist in other volcanic regions. The peoples of Indonesia, living among some of the most active volcanoes on the planet, have developed extensive traditions for understanding and responding to volcanic activity. The Japanese, with their many sacred mountains, including the actively volcanic Mount Fuji and others, have integrated volcanic phenomena into their religious traditions in elaborate ways. The peoples of Mesoamerica, living among numerous volcanoes that have shaped their landscapes for thousands of years, developed religious frameworks that included specific deities associated with volcanic activity and specific practices for maintaining proper relationships with these forces. The pattern is consistent across volcanic regions of the world. Cultures that live with active volcanoes develop frameworks for understanding the volcanoes as participants in the cosmic order rather than as merely physical phenomena. And these frameworks provide both explanatory accounts and practical guidance for how to live with the periodic dramatic events that volcanic activity produces. There is one more aspect of volcanic mountains that I want to address. The supervolcanoes are a category of volcanic system that operate on scales far larger than ordinary volcanoes, with eruptions that can affect the entire planet for years or decades. The Yellowstone caldera in the western United States is one of the most studied supervolcanoes in the world. The system has erupted 3 times in the past 2 million years, with each eruption producing massive quantities of ash and other materials that affected continental and global climate. The most recent supervolcanic eruption at Yellowstone, approximately 640,000 years ago, ejected approximately 1,000 cubic kilometers of material, dwarfing any volcanic eruption in human historical memory. If a similar eruption were to occur today, it would have catastrophic consequences for global civilization, with widespread crop failures, atmospheric effects, and direct destruction across substantial portions of North America. The Yellowstone system is currently in a relatively quiet phase, with regular geothermal activity, but no signs of imminent supervolcanic eruption. But the history of the system, with its recurring cycles of supervolcanic activity, means that another major eruption is essentially certain at some point in the geological future, even though the timing cannot be predicted with current methods. Other supervolcano systems exist around the world, including in places like the Toba caldera in Indonesia, which erupted approximately 74,000 years ago in what may have been the largest volcanic eruption of the past 2 million years. The Toba eruption ejected so much material into the atmosphere that some researchers have proposed it caused a significant decline in human population, with our ancestors being reduced to a small fraction of their previous numbers. This volcanic winter hypothesis is contested, with some researchers arguing that the human impact of the Toba eruption was less severe than the original proposal suggested. But the scale of the eruption itself is not in dispute. It was a genuinely massive event that affected the global atmosphere and probably had substantial consequences for ecosystems and human populations across large portions of the world. So as you continue to drift, hold this image in your mind: a volcanic mountain in some quiet phase of its existence, perhaps Mount Fuji in Japan, or one of the active Hawaiian volcanoes, or one of the many active volcanoes of the Pacific Ring of Fire. The mountain stands quietly tonight, with its slopes covered in whatever vegetation has been able to colonize the volcanic soils. The communities that live in its shadow are sleeping, in the relatively brief moments of human history that fall between volcanic events. The mountain has erupted in the past and will erupt again in the future, but for now it is quiet, with whatever internal processes are continuing within it being invisible to surface observers. The cultural traditions that the local people have developed in relation to the mountain continue to be maintained, with the appropriate respects being paid to the volcanic forces that the mountain represents. The mountain operates on its own timescale, with periods of quiet stretching between volcanic events that can last for centuries or millennia. The human communities adapt their lives to this rhythm, building and farming and living in the productive periods between eruptions, then responding when the eruptions come, then rebuilding afterward in cycles that have continued for as long as humans have lived in volcanic regions. Tonight, like every night, the volcanic mountains stand. Tonight, like every night, the relationships between these mountains and the human communities that live near them continue, in patterns of patient waiting and occasional dramatic interaction that have characterized the human experience of volcanic landscapes throughout our history. Tonight, I want to take you into a category of mountain that affects nearly every aspect of how mountains have functioned in human and natural history, and that has been transformed dramatically in our own lifetime. I want to talk about the ice and snow of mountains, the glaciers and snowfields, and frozen environments that exist at high elevations across the world, and what they mean for the planet and for the communities that depend on them. Because the ice of mountains is not just frozen water at high altitude. It is one of the most important features of the planet's water cycle, one of the most sensitive indicators of climate change, and one of the most rapidly transforming aspects of the modern world. Let me start with what mountain glaciers actually are and how they form. A glacier is essentially a river of ice, formed when snow accumulates in mountain regions over many years and gradually compacts into solid ice that flows slowly downhill under its own weight. The process begins with snowfall in high elevation areas where temperatures remain cold enough that the accumulated snow does not fully melt during the warmer seasons. As more snow accumulates on top of older snow, the lower layers are compressed by the weight above them, eventually being transformed into ice through a slow process of compaction and recrystallization. The resulting ice, when it accumulates to sufficient thickness, begins to flow downhill in response to gravity, with the rate of flow depending on the thickness of the ice, the steepness of the underlying terrain, and various other factors. The ice typically moves at rates of meters per year, though some particularly active glaciers can move much faster, with rates of hundreds of meters per year being recorded in extreme cases. The mechanics of glacier flow are genuinely strange when you consider them carefully. Ice, despite being a solid material, behaves like a very viscous fluid when it accumulates in sufficient quantities. The pressure of the ice above causes the deeper layers to deform plastically, flowing slowly without breaking. The result is that an entire mass of ice, which might weigh billions of tons, moves coherently down its valley like an extraordinarily slow river. The ice flows around obstacles, splits into separate streams when terrain divides, and merges back together when conditions permit. The whole process operates on timescales that are imperceptible to human observation in any single moment, but that produce dramatic effects when integrated over years and decades. A glacier, visible at one point on a mountain today, is not the same ice that was there 100 years ago. The ice has flowed forward, with new ice forming above and old ice melting or breaking off below, in a continuous slow movement that gradually transports material from the upper accumulation zone to the lower melting zone. The effects of glacier flow on the underlying landscape are substantial. As glaciers move, they grind against the bedrock beneath them, picking up rocks and sediments and carrying these materials along with the flowing ice. The grinding action carves deep U-shaped valleys, plucks rocks from underlying surfaces, and transports vast quantities of material from upper to lower elevations. Many of the most dramatic mountain landscapes were carved by glacial action during past ice ages, when glaciers were much more extensive than they are today. The fjords of Norway, the glacial valleys of the Alps, and the dramatic landscapes of the Canadian Rockies all bear the marks of past glacial activity, with their characteristic shapes reflecting the work of ice that may no longer be present, but that left lasting evidence of its passage. The water stored in mountain glaciers is enormous, and its release through gradual melting plays a crucial role in the water cycles of regions across the planet. The glaciers of the Himalayas alone store enough water to substantially affect the river systems of South and Southeast Asia, with the Ganges, the Indus, the Brahmaputra, the Mekong, and other major rivers all drawing significant portions of their flow from glacial sources. The Andean glaciers similarly support river systems that flow eastward into the Amazon basin and westward to the Pacific coast, providing water for human populations and ecosystems throughout South America. The alpine glaciers feed the Rhine, the Rhone, the Danube, and other major European rivers. Glaciers in western North America support rivers flowing into the Pacific and into the major drainage systems of the continent's interior. The cumulative effect is that hundreds of millions of people, perhaps billions, depend on water that originates in mountain glaciers, even though most of these people may never see the actual glaciers themselves. The seasonal pattern of glacial water release is particularly important for human and ecological systems. Glaciers store water during the winter when snow accumulates at high elevations, and release water during the warmer months when temperatures are high enough to melt the ice and snow. The timing of this release coincides with the periods of highest agricultural water demand in many regions, providing irrigation water during the growing season when it is most needed. Many of the world's major agricultural regions depend on this seasonal pattern, with the gradual melting of mountain ice providing reliable water supplies that support food production for substantial human populations. The relationship between mountain glaciers and lowland agriculture has been one of the most important ecological relationships in human civilization, with civilizations rising and falling partly in response to changes in the availability of glacier-derived water. I want to address now what is happening to mountain glaciers in the current era, because this is one of the most rapidly changing aspects of the planet's surface. Mountain glaciers around the world are retreating, in most cases dramatically, in response to global climate change. The retreat has been occurring for decades, but it has accelerated in recent years as global temperatures have continued to rise. Some smaller glaciers have already disappeared entirely, while many others are projected to disappear within the coming decades. The rate of glacial loss varies across regions, with some glaciers losing many meters of length per year, and others losing primarily through thinning rather than retreat of their leading edges. The cumulative effect, however, is consistent across most regions of the world. The mountain glaciers that have existed for thousands of years are now shrinking rapidly, with consequences that are still being worked out. The implications of glacial retreat for human and ecological systems are substantial. The reduction in glacial ice means that the seasonal water releases that have supported agriculture and ecosystems for thousands of years are changing in both timing and magnitude. In the short term, increased melting can actually produce more water in the rivers downstream from retreating glaciers, as the accumulated ice melts more rapidly than usual. In the longer term, however, as the glaciers disappear, the water supplies they provided are reduced or eliminated. River systems that have depended on glacial sources for their flow patterns are facing fundamental changes, with implications for agriculture, fisheries, hydroelectric power, and various other human activities that depend on reliable water supplies. The communities and ecosystems that have developed around glacier-fed rivers are facing transitions that will require substantial adaptations, with the specifics depending on how rapidly the glaciers disappear and what alternative water sources may be available. Beyond the immediate effects on water supplies, the disappearance of mountain glaciers has cultural and psychological dimensions that should not be overlooked. The communities that have lived in proximity to mountain glaciers for many generations have often developed cultural relationships with these features that go beyond their practical utility. The glaciers have been understood as sacred, as ancestral presences, as features of the landscape that contribute to the identity of the local communities. The disappearance of these glaciers therefore represents not just a practical loss of water resources, but a cultural loss of features that have been part of the local landscape for as long as the local cultural memory extends. The glaciers of the Andes, the Himalayas, and other regions are not just frozen water. They are participants in the cosmologies of the peoples who have lived among them, and their disappearance is being experienced as more than a practical environmental change. It is being experienced as a kind of ending, with the landscape that the local cultures developed within being fundamentally transformed in ways that previous generations could not have anticipated. I want to bring in here something that I find genuinely poignant about the current situation. The glaciers that are disappearing now formed thousands of years ago, in climate conditions different from those of the present. They have endured through countless human generations, providing water and shaping landscapes and participating in the lives of the human communities that have lived near them. They are now disappearing within the span of a few decades in a transformation that is occurring within a single human lifetime. The people who saw these glaciers in their childhood are watching them disappear in their old age. The people whose grandparents knew these glaciers as permanent features of the landscape are now telling their grandchildren about features that may not exist by the time those grandchildren reach adulthood. The pace of the transformation is unprecedented in human historical memory, and the experience of watching ancient features disappear within a few decades is one of the genuinely difficult aspects of the current moment in human history. The science of glacier monitoring has developed substantial sophistication in recent decades, with satellite measurements, aerial photography, ground-based monitoring stations, and various other techniques being used to document the changes that are occurring. The data is essentially unambiguous. Across most regions of the world, glaciers are losing mass, retreating, thinning, and in some cases disappearing entirely. The trends have continued and accelerated despite international efforts to address climate change, with the cumulative effects of past emissions producing changes that will continue for decades, regardless of what mitigation efforts are undertaken in the present. The disappearance of substantial portions of the world's mountain glaciers is essentially certain over the coming century, with the only questions being how rapidly the changes will occur and what specific glaciers will survive in modified forms versus those that will be lost entirely. There is one more aspect of mountain ice that I want to address before we close this part. The ice and snow of mountains contains records of past climate conditions that provide some of our best evidence about how the planet's climate has changed across deep time. The ice cores extracted from mountain glaciers contain trapped air bubbles from the periods when the ice formed, with the chemistry of those bubbles providing direct information about the atmospheric conditions of the past. The ice also contains layers that can be counted like tree rings, with each layer representing a year of accumulation. The chemistry of the layers, including the ratios of various isotopes, provides additional information about temperature, precipitation, and other climate variables in the past. The longest ice core records, from the deepest accumulations of mountain ice, extend back hundreds of thousands of years, providing direct evidence about the climate of the planet during the entire span of modern human existence. As the glaciers disappear, the ice records they contain are being lost, with the climate history they preserved being permanently inaccessible after the ice melts. The disappearance of mountain glaciers is therefore not just an ecological and cultural loss, but also a loss of scientific records that cannot be replaced. So as you continue to drift, hold this image in your mind. A high mountain valley, somewhere in the world, perhaps in the Alps, or the Andes, or the Himalayas, in the middle of a winter night. The glacier that occupies the upper portion of the valley is mostly invisible in the darkness, with only its general outlines being suggested by the lighter color of the snow and ice against the surrounding rock. The ice has been here for thousands of years, with the oldest portions at the bottom of the glacier having formed during the last ice age and having been slowly flowing downhill ever since. Tonight, even in the cold of winter, the glacier is changing. Subtle thermal effects, the result of relatively warm conditions during the previous summer, continue to affect the ice. Meltwater from the warmer months has refrozen in cracks and crevasses, redistributing mass within the ice mass. The whole glacier is participating in the slow reduction that has characterized its recent history, with each year's accumulation now generally being less than the previous year's loss. The communities downstream from the valley in the lowlands far below depend on this glacier for water that has supported their agriculture and their ways of life for many generations. They are sleeping tonight, mostly unaware of what is happening to the ice high above them, but the changes are occurring nonetheless. By the time their grandchildren are adults, the glacier may be substantially smaller than it is tonight, or it may be gone entirely. The communities will have to adapt, in whatever ways prove possible, to a world in which the ancient ice of the mountains is no longer providing the resources it has provided for so long. Tonight, however, the ice is still here, Tonight, the glacier still occupies its valley. Tonight, the slow processes continue in the patterns that have characterized the planet's mountain regions for thousands of years, even as those patterns are being transformed by the changes that are occurring around them. Tonight, I want to take you into a question that has been quietly underlying everything we have been discussing, but that I want to address directly now. The question concerns the relationship between mountains and human imagination, and specifically why mountains have been such powerful sites for the development of myth, story, and narrative across virtually every culture that has lived in their presence. Because the pattern is genuinely striking. When you survey the storytelling traditions of the world, you find that mountains appear with remarkable frequency as settings for transformative experiences, as homes of supernatural beings, as locations of cosmic significance, and as features that organize the geographical imagination of the cultures that produce the stories. Tonight, I want to walk you through some of these patterns, what they may tell us about the human relationship with mountains, and what the persistence of these patterns suggests about how mountains affect human consciousness. Let me start with one of the most consistent patterns in mountain storytelling. Mountains are, across an enormous range of cultures, the places where humans encounter beings or experiences that lie beyond the boundaries of ordinary existence. The pattern recurs in tradition after tradition with such consistency that it cannot be dismissed as coincidence. Moses ascends Mount Sinai and encounters the divine voice that gives him the law for his people. Jesus retreats to mountains for periods of prayer and is said to have undergone the transfiguration on a mountain in the presence of his disciples. Muhammad receives his first revelations in a cave on Mount Hira. The Buddha achieves significant moments of his spiritual development in mountain locations. The various sages of Taoism are traditionally associated with mountain retreats where they cultivated their spiritual capacities. The shamans of Siberian and Mongolian traditions ascend ritual mountains in their journeys between ordinary reality and the spirit world. The pattern of the mountain as a site of contact with what lies beyond ordinary experience is so widespread that it must reflect something fundamental about the human relationship with elevated terrain. Why should this pattern be so consistent? Several factors probably contribute. The physical experience of being at high elevation produces altered states of consciousness through the reduced atmospheric oxygen, with effects that range from mild euphoria to substantial cognitive changes depending on the elevation and the individual's adaptation. Ancient peoples who climbed to the high mountains, whether for practical or religious purposes, would have experienced these altered states without having any framework for understanding them as products of physiology. The experiences would have seemed to be features of the mountain environment itself, with the high terrain providing access to forms of consciousness that were not available at lower elevations. The interpretation of the high mountains as sites of spiritual significance therefore had a basis in actual experiential differences, even if the original interpreters did not understand the mechanisms producing those differences. But the physiological explanation, while it captures something real, may not be the full account of why mountains have been such consistent sites of imaginative significance. Mountains also have specific visual and atmospheric qualities that probably contribute to their imaginative resonance. The combination of vast scale, elevated horizon, dramatic weather phenomena, and accessible inaccessibility produces a particular kind of landscape that probably activates specific cognitive and emotional responses in humans. When you stand at the base of a major mountain, looking up at peaks that rise far above you, the experience produces a sense of magnitude and presence that does not occur in ordinary landscapes. The peaks are visible but unreachable. The terrain is familiar but extreme. The atmosphere is the same atmosphere we breathe at lower elevations, but it is also somehow different, thinner and clearer, and producing different perceptual effects. The combination of these qualities produces a perceptual experience that is genuinely distinct from ordinary terrestrial experience, and that probably contributes to why mountains have been understood as occupying a special category in human imaginative geography. I want to bring in here some specific examples of mountain stories from different traditions, because the specific stories illuminate the patterns better than abstract descriptions can. In the Greek tradition, Mount Olympus is the home of the gods, with each of the major Olympian deities having a specific dwelling on the mountain. The geography of Olympus in the Greek imagination is detailed and specific, with the mountain functioning as a kind of cosmic council chamber, where the gods deliberate, dispute, and conduct their affairs. Mortal humans cannot ascend to Olympus, but the gods can descend to interact with mortals, with the mountain serving as the boundary between the divine and human realms. The pattern of the mountain as the home of the gods, with humans being barred from its summit, but the gods being able to descend, is a recurring structure that appears in many traditions beyond the Greek. In the Norse tradition, Asgard, the home of the gods, is similarly understood as elevated, with the rainbow bridge Bifrost connecting the world of the gods to the world of humans. The cosmic geography of Norse mythology includes various other elevated sites, with mountains playing roles in the locations of giants, dwarves, and other supernatural beings. The Yggdrasil, the world tree that connects the various realms of Norse cosmology, has roots and branches that reach into different cosmic locations, with the structure of the cosmos being organized vertically in ways that probably draw on the imaginative resonance of mountain elevation. The Norse tradition, like the Greek, treats elevation as a cosmic principle, with higher locations being associated with more sacred or powerful beings, and lower locations with more ordinary or unfortunate ones. In the various Hindu traditions, the cosmic geography is organized around Mount Meru, the central cosmic mountain that stands at the center of the universe. Meru is understood to be vastly larger than any physical mountain, with multiple peaks rising to heights that exceed any earthly elevation. Various worlds and realms are arranged around Meru, with the gods and various other beings occupying specific locations relative to the cosmic mountain. The physical mountains of the Himalayas have been understood as manifestations of the cosmic Meru, with specific peaks being identified as physical instances of the cosmic principle. The relationship between the cosmic geography and the physical landscape is therefore close in the Hindu tradition, with the actual mountains of South Asia being understood as participating in the cosmic geography rather than being separate from it. The Chinese cosmological tradition includes the 5 sacred mountains, which mark the cardinal directions and the center of the cosmos in traditional Chinese geography. Each of the 5 mountains has specific religious associations and has been the site of imperial pilgrimages and rituals throughout Chinese history. The cosmic geography is organized around the 5 mountains in ways that integrated the physical landscape into the political and religious order of the empire. The mountains themselves have continued to be sites of pilgrimage and religious activity into the present, with millions of visitors making the ascent of these peaks each year as part of practices that have continued for thousands of years. In the various indigenous traditions of the Americas, mountains have been similarly central to cosmic geography, with specific peaks being understood as occupying cosmically significant positions. The Navajo tradition includes 4 sacred mountains that mark the boundaries of the traditional Navajo homeland, with each mountain being associated with specific deities, directions, and ceremonial functions. The Lakota tradition treats the Black Hills of South Dakota as sacred, with specific sites within the hills having particular religious significance. The Andean tradition we discussed in earlier parts treats specific peaks as living apus with their own personalities and powers. Across the indigenous traditions of the Americas, mountains have consistently been understood as cosmically significant, with the traditional ceremonies and stories of these traditions developing in close relationship with the physical mountain landscapes. I want to address something specific that recurs in mountain storytelling traditions across cultures. The pattern of the hero who ascends a mountain and is fundamentally transformed by the experience appears with remarkable frequency. The transformation can take various forms. The hero may receive new knowledge or understanding. The hero may be initiated into spiritual capacities that were not previously available. The hero may be tested by various challenges encountered on the mountain. The hero may meet supernatural beings who provide guidance or transmission of significant teachings. The hero may experience a kind of death and rebirth, returning to ordinary society as a transformed person who is now capable of providing leadership or wisdom that was not previously available. The pattern is so widespread that the comparative mythologist Joseph Campbell incorporated it into his analysis of the hero's journey, with the mountain ascent representing a particularly common version of the basic narrative structure that he argued underlies myths from many cultures. The persistence of the mountain ascent as a transformative narrative pattern probably reflects something about the actual experience of climbing mountains. The physical challenges of mountain ascent, the changes in perspective that elevation produces, the encounter with environments that differ substantially from ordinary lowland conditions, the achievement of summit views that show the surrounding world from new vantage points, all combine to produce experiences that have transformative qualities even for ordinary contemporary climbers. The traditional stories are probably reflecting and elaborating on the actual psychological effects of mountain ascent, framing those effects within the cosmological and religious frameworks of the various cultures, and producing narratives that resonate with the experiences that mountain climbing actually produces. I want to bring in here something that I find genuinely interesting about the modern relationship with mountain narratives. The traditional religious frameworks within which mountain stories developed have been substantially weakened in modern industrial societies, but the narrative resonance of mountains has not disappeared. Modern literature, film, and popular culture continue to use mountains as settings for transformative experiences, with the specific religious or cosmological frameworks being replaced by more secular versions of the same basic narrative structures. The mountain climber who confronts personal demons on a difficult ascent, the spiritual seeker who retreats to a mountain location to pursue understanding, the ordinary person whose life is changed by an encounter with mountain wilderness, all represent modern versions of the ancient patterns. The specific religious content has often been removed or transformed, but the underlying recognition of mountains as sites of transformation has continued. The persistence of these patterns suggests that something about the human relationship with mountains operates at a level deeper than specific cultural or religious frameworks, with the imaginative resonance of mountains continuing to shape modern stories, even when the original religious content has been set aside. There is one more aspect of mountains and imagination that I want to address. The mountains as physical features are essentially permanent on human timescales, but the cultural meanings attached to them have been subject to substantial change over time. Specific mountains that have been understood as sacred in one cultural framework have been reinterpreted within different frameworks as cultures changed or as new populations moved into mountain regions. The same physical mountain may have been understood as the home of one set of deities in one period, as a Christian holy site in a later period, and as a tourist destination in the present. The continuity of the physical mountain across these cultural transformations is striking, with the actual peaks remaining essentially unchanged, while the human meanings attached to them have shifted dramatically. The mountain itself, in some sense, is indifferent to the various cultural frameworks that have been applied to it. It continues to exist in its slow geological way, regardless of how human cultures choose to understand it. The various meanings come and go in the relatively rapid pace of cultural change, while the mountain itself persists. So as you continue to drift, hold this image in your mind. A mountain peak somewhere in the world, perhaps a peak that has been understood as sacred in some traditional culture, perhaps a peak that is now primarily a destination for tourists and climbers, perhaps a peak that has yet to be fully integrated into any specific cultural framework. The mountain stands in the night, in the same configuration it has stood for thousands of years. Throughout its history of being known to humans, various stories have been told about it. Various deities or spirits have been associated with it. Various ceremonies have been conducted at its base or on its slopes. Various climbers have ascended it for various purposes. Various meanings have been attached to it by various human communities. The mountain has not changed in any way that responds to these human activities. It has stood in its slow geological way, while the cultural meanings have shifted around it. Tonight, like every night, somewhere in the world, someone is telling a story about a mountain. Someone is climbing toward a summit for reasons that connect to ancient patterns of mountain narrative. Someone is having a transformative experience in mountain wilderness that fits the basic structure of the traditional mountain ascent story. The patterns continue, even when the people involved do not consciously connect what they are doing to the long human tradition of mountain narrative. The patterns are deep in the human relationship with mountains, and they continue to shape how humans engage with elevated terrain, regardless of the specific cultural frameworks within which the engagement occurs. The mountains stand, the stories continue. The relationship between human imagination and mountain landscape persists in the patterns that have characterized this relationship throughout the long human past. We come now to the closing part of our long exploration, and I want to use it to draw together what we have been discovering across these many hours, and to leave you with the right kind of questions to carry into the sleep that is now, I hope, very close. Because the cumulative weight of everything we have examined tonight points toward a picture of mountains that is far richer, far stranger, and far more genuinely interesting than the casual encounter with mountain scenery would suggest. And the picture has implications for how we should understand our place on this planet and our relationship with the long natural processes that have shaped it. What have we actually been doing across these many hours of patient examination? We have been walking around the edges of one of the most familiar, yet most genuinely strange features of the planet, and noticing aspects of mountains that the casual treatment usually overlooks. We began with the basic question of what a mountain actually is, and we found that even this seemingly simple question turns out to involve fuzzy boundaries between physical characteristics and cultural conventions. We examined how mountains form through the slow movement of tectonic plates, with the Himalayas providing a dramatic example of continental collision, and the Andes providing a different kind of example involving subduction and volcanic activity. We considered the dramatic effects that mountains have on climate and weather, with their roles in producing rain shadows, monsoons, and the various atmospheric patterns that shape regional ecologies and human civilizations. We looked at how life has colonized mountain environments, with the remarkable adaptations of plants and animals that allow them to thrive in conditions that would be impossible for most species. We considered the cultural and religious significance that mountains have held across virtually every human tradition that has lived in their presence, with the consistent patterns of mountain veneration suggesting something deep about the human relationship with elevated terrain. We examined the volcanic mountains as a different category from tectonic ranges, with their specific dramatic events shaping both the landscapes and the cultures that live near them. We address the ice and snow of mountains, with their crucial role in water cycles and their rapid transformation in the current period of climate change. And we considered how mountains have functioned as sites for the development of myth and story across human cultures, with consistent patterns of mountain narrative reflecting both the physical experiences of mountain environments and the imaginative responses that mountains evoke in human consciousness. Each of these topics, taken individually, is interesting. Taken together, they form a picture that I want to articulate carefully now. The picture is that mountains are not simply impressive features of the landscape. They are dynamic geological structures, climate engines, biological habitats, cultural symbols, and imaginative resources, all at the same time. They participate in the planet's systems on multiple levels simultaneously, with their physical presence affecting weather and biology and human history in ways that interconnect across the full range of natural and cultural phenomena. The mountains we see, when we encounter them in our brief human moments, are the visible expression of vast processes operating on timescales far longer than human existence, with the present configuration of any mountain range being a snapshot of an ongoing transformation that began long before any humans existed and that will continue long after we are gone. This recognition has implications that I think are worth sitting with carefully. The first implication is that we are temporary observers of features that operate on timescales we can barely comprehend. Mountains have been forming and eroding across the surface of this planet for hundreds of millions of years, with the specific ranges we now see being only the current configuration of an ongoing process. The Himalayas continue to rise, the Appalachians continue to erode, new volcanoes continue to emerge while old ones become extinct. The mountains we know are part of a continuous geological evolution that we are privileged to glimpse during our brief presence on the planet, but that we cannot really hold steady or fully comprehend during the relatively short spans of our individual lives, or even our cultural histories. The second implication is that our relationship with mountains is a relationship with deep time. When we stand before a mountain, we are encountering something that has existed in roughly its current form for vastly longer than any human civilization has existed. The mountains have witnessed, in their geological way, the rise and fall of multiple human cultures, the emergence and disappearance of numerous biological species, the comings and goings of climates and ice ages, and various other planetary events that occurred long before any humans were present to observe them. The mountains are, in some sense, the slowest witnesses on the planet's surface, recording in their structures and positions the long history of the planet that produced them. The careful attention to mountains is therefore a kind of attention to deep time itself, with the mountains providing a tangible connection to processes that operate at timescales we can barely conceptualize. The third implication is that the meanings we attach to mountains are themselves part of a long human tradition that connects us to all the previous generations who have lived in their presence. The various religious and cultural frameworks that we have examined did not appear in isolation from each other, even when they developed in cultures that supposedly had no direct contact. They reflect consistent human responses to the experience of being in proximity to elevated terrain, with similar patterns recurring across cultures that supposedly developed independently. When you stand before a mountain today and feel something significant about the encounter, you are participating in a pattern of human response that connects you to countless previous generations of humans who stood before similar mountains and experienced similar significance. The connection is real, even though we have largely lost the specific cultural frameworks within which our ancestors originally interpreted these experiences. The fourth implication, and the one I want to leave you with, concerns how mountains might inform how we live our brief human lives. The mountains have a way of putting human concerns in perspective. They are large enough, old enough, and indifferent enough to our specific situations that they cannot help but contextualize our individual struggles within a much larger frame. The various concerns that occupy our daily lives, the stresses and ambitions and disappointments and hopes, are real and significant in their own contexts, but they exist on a scale that is dwarfed by the scale of mountain time and mountain process. This contextualization can be experienced as humbling or as liberating, depending on the disposition with which it is received. The mountains do not solve our problems, but they provide a frame within which our problems can be seen as the human scale concerns that they are, occurring within a much larger natural order that contains them but does not depend on them. There is something almost spiritual about this when you sit with it carefully, although I do not want to push the language too far in any specific direction. The traditional cultures that developed religious frameworks for understanding mountains were responding, in their own ways, to the contextualizing function that mountains naturally provide. The recognition that one's own life occurs within a vast natural order that vastly exceeds it, and that has its own integrity independent of human concerns, is one of the recurring elements in religious and contemplative traditions across cultures. The mountains provide a particularly tangible example of this larger order, with their physical presence making concrete what other contemplative practices may achieve through more abstract means. The careful attention to mountains is, in this sense, a kind of natural contemplative practice, available to anyone who lives within sight of significant mountains, and who is willing to allow the mountains to do their slow work on the human attention. There is one final thought I want to leave you with as we close this exploration. The mountains we have been discussing are not finished. They continue to exist, to form, to erode, to participate in the planet's ongoing geological evolution. The future of any specific mountain range depends on the interplay of forces that build it up and forces that wear it down, with the specific patterns of change being predictable in broad outlines, but not in detailed specifics. The Himalayas will continue to rise for many millions of years. The Appalachians will continue to erode. New volcanoes will continue to emerge in the active zones of the planet. The mountains of the future will be different from the mountains of the present, just as the mountains of the present are different from the mountains of the past. The story of the planet's mountains is not over. It continues to unfold, on its own slow schedule, in patterns that no human will live long enough to fully observe, but that will continue regardless of human observation. We are participants in this larger story for the brief moments that constitute our individual lives, and the participation is real, even if it is partial. The mountains stand in our presence. We acknowledge them in whatever ways we can. The acknowledgement is part of how we briefly inhabit this strange and beautiful planet. If you have found this exploration valuable, if the patient walk through the long story of mountains has given you something to carry with you as you finally drift off, please consider letting me know in the comments below. Tell me what struck you most. what questions you would like to explore further, what other deep mysteries you would like to spend a long, quiet night thinking about. Subscribe to Sleepy Tin Foil Hat if the channel is the kind of thing you want more of, because the channel exists for the audience that wants this slow, careful kind of thinking. And the audience tells the algorithm we are here through the small acts of comment and subscription. The community of careful nighttime thinkers is scattered across many time zones and many lives, and the way we find each other and keep this work going is through these small signals. Sleep well. Let yourself go gently. The mountains we have been discussing tonight will still be standing in the morning, as they have been standing for thousands and millions of years, indifferent to whether any particular thinker is awake or asleep at any particular hour. They will continue to stand through the night that is now waiting for you, performing their slow work of erosion and uplift and weather production, while you perform your own brief work of falling asleep and waking up in the morning. The connection between your small human moment and the vast patient time of the mountains is real, even though it is asymmetric in the extreme. The mountains do not need your attention, but your attention to them, when you offer it, connects you to one of the most genuinely significant features of the planet you live on, and to all the previous humans who have offered similar attention across the long history of our species. Tonight, like every night, the mountains stand. Tonight, like every night, somewhere in the world, someone is looking at them and feeling something significant about the encounter. Tonight, like every night, you are joining the long human practice of paying attention to the slow and the large and the patient, in a brief act of human awareness that places your moment within the much longer story of the planet that produced you. The story will continue in the morning when you wake, and the mountains, having stood through the night that you are about to give yourself to, will be there waiting in their slow geological way when you and I both turn our attention to other matters in the morning. Tonight I want to take you into a question that has been quietly underlying our exploration, but that I want to address directly now. The question is, what mountains do to the air, the weather, and the climate, and how their effects on these systems have shaped the development of life and human civilization across the planet. Because mountains are not just impressive features of the landscape. They are atmospheric engines, climate engines, weather engines that fundamentally reshape the conditions of the region surrounding them. And the effects extend far beyond the immediate vicinity of the peaks themselves, reaching across continents and oceans in ways that have determined where rain falls, where deserts form, where forests grow, and where human civilizations have been able to develop. Let me start with the most basic interaction between mountains and the atmosphere. When air masses encounter a mountain range, they cannot simply pass through. They have to go up, around, or through gaps in the terrain. The behavior of the air as it interacts with the mountain barrier determines a great deal about the weather and climate patterns that develop on either side. When prevailing winds carry moist air toward a mountain range, the air is forced upward as it encounters the rising terrain. As air rises, it cools, because atmospheric pressure decreases with elevation and air expands as pressure decreases, with the expansion causing cooling. As the air cools, its capacity to hold water vapor decreases, and the water vapor begins to condense into clouds and eventually into precipitation. The result is that the windward side of mountain ranges, the side facing the prevailing winds, tends to receive substantial rainfall, supporting forests, lush vegetation, and the various ecosystems that depend on regular precipitation. The leeward side of the same mountain range, the side away from the prevailing winds, has a very different climate, By the time air has crossed the mountain barrier, it has lost much of its moisture as precipitation on the windward slopes. The air that descends on the leeward side is drier than it was before encountering the mountains, and as it descends, it warms due to compression. The combination of dry air and warming temperatures produces what is called a rain shadow, a region of reduced precipitation on the leeward side of mountains, where conditions can range from semi-arid to extremely dry. Many of the world's major deserts exist specifically because of rain shadow effects produced by nearby mountain ranges. The Atacama Desert in northern Chile and southern Peru is one of the most extreme examples of a rain shadow desert. The Andes block moisture from the Atlantic Ocean and the Amazon basin from reaching the western coast, while a different atmospheric circulation pattern reduces moisture coming from the Pacific. The result is one of the driest places on Earth, with some weather stations in the Atacama having recorded essentially no rainfall in centuries of measurement. The desert is so dry that scientists have used parts of it as analogues for the surface of Mars when testing equipment for extraterrestrial exploration. Yet just a few hundred kilometers to the east, on the other side of the Andes, the Amazon basin receives some of the highest rainfall on the planet, with the same atmospheric system that produces the desert producing the rainforest. The mountains in between determine which region gets the rain and which region does not, with consequences for everything from local ecology to the patterns of human settlement. The Himalayas similarly produce dramatic climate effects across Asia. The southern slopes of the Himalayas receive the heavy summer monsoon rains that drench the Indian subcontinent, while the Tibetan plateau to the north of the mountains lies in their rain shadow and receives much less precipitation. The agricultural systems of South Asia, supporting more than 1 billion people, depend on the monsoon rains that the mountains help to produce. The grasslands and deserts of Central Asia, by contrast, exist in the dry conditions that the mountains help to maintain by blocking moisture from reaching them. The whole climate of the Asian continent has been shaped by the presence of the Himalayan barrier, and the rise of these mountains over the past 50 million years has progressively reshaped the climate of the entire region. Mountains also affect atmospheric circulation in ways that go beyond simple rain shadow effects. The high terrain of major mountain ranges acts as an obstacle to the broader patterns of atmospheric flow, redirecting winds, producing characteristic standing wave patterns in the atmosphere, and influencing the development of weather systems across large regions. The jet streams, the high-altitude rivers of fast-moving air that play important roles in determining weather patterns across the middle latitudes, are themselves influenced by the position and height of major mountain ranges. The Tibetan Plateau, in particular, has substantial effects on the atmospheric circulation across the entire northern hemisphere, with the heating and cooling of this large elevated landmass producing seasonal patterns that affect weather thousands of kilometers away. I want to bring in here something genuinely interesting about how mountains affect climate at smaller scales. The microclimates that exist on individual mountains can vary dramatically across short distances, with conditions on one side of a peak being substantially different from conditions on the other side. The differences in temperature, precipitation, wind exposure, and sunlight can produce strikingly different ecosystems within sight of each other on the same mountain. This produces what biologists call zonation, the clear bands of different vegetation types that can often be seen on mountain slopes, with different species occupying different elevation ranges according to their specific tolerances for the local conditions. As you climb a mountain, you typically pass through a series of distinct ecological zones, with the transitions between them sometimes being remarkably abrupt, marking the boundaries where specific climate conditions favor one type of vegetation over another. The patterns of mountain zonation are similar in their general structure across many parts of the world, even though the specific species involved differ from region to region. The lowest zones typically support forests adapted to relatively warm and moist conditions. As elevation increases, these forests give way to forests of different species adapted to cooler conditions. Eventually, the elevation becomes too cold for trees, and the tree line marks the transition to alpine grasslands, or shrublands. Above the alpine zone, conditions become too harsh even for low vegetation, and the upper elevations of high mountains support only specialized plants that can tolerate extreme cold, wind, and limited growing seasons. At the highest elevations, conditions become too extreme for any vegetation at all, and the rocky, barren zones near the summits support only the most specialized organisms, including various microbes and a few insects and birds adapted to the conditions. Climbing a mountain, therefore, is in some sense like traveling across latitudes from temperate to polar regions, with each 1,000 meters of elevation roughly equivalent to traveling several hundred kilometers toward the pole. This equivalence is rough, and it varies with specific local conditions, but it captures something important about the relationship between elevation and climate. A high mountain in a tropical region can have Arctic conditions at its summit, with the various ecological zones along its slopes, corresponding to the climate zones found at increasing distances from the equator. The biological diversity of mountain regions is partly a result of this compression of climate zones into vertical space, with the slopes of a single mountain potentially supporting the kinds of biological diversity that would normally require a much larger horizontal area to develop. I want to address now something that affects everyone who has ever spent significant time at high elevation, including the people who live in mountain regions and the visitors who come to climb or explore. The atmospheric pressure decreases with elevation, which means that the partial pressure of oxygen in the air also decreases with elevation. At sea level, the atmospheric pressure is sufficient to provide ample oxygen for normal human metabolism. At high elevations, the reduced pressure means that each breath provides less oxygen to the body, with consequences that range from mild discomfort to serious illness depending on the elevation and the individual's adaptation. The effects begin to become noticeable for most people at elevations above about 2,500 meters, and they become serious at elevations above 3,500 meters. The human body responds to high altitude through a series of physiological adaptations that work to compensate for the reduced oxygen availability. In the short term, the body increases its breathing rate and heart rate to deliver more oxygen to the tissues. The body also begins producing more red blood cells over the course of days and weeks, increasing the oxygen-carrying capacity of the blood. The kidneys adjust their function to compensate for various other physiological changes induced by the altitude. These adaptations can be substantial, and people who spend extended time at high elevations can become acclimatized to conditions that would be debilitating to unacclimatized visitors. But the adaptations are not unlimited. Above about 5,500 meters, the human body cannot fully adapt, and prolonged stays at such elevations result in progressive deterioration of health, regardless of acclimatization. The peoples who live at the highest elevations on Earth, in the Tibetan and Andean highlands, generally live below about 4,500 meters, with even more elevated terrain being used only seasonally or for specific purposes, rather than for permanent settlement. The biological adaptations of high-altitude human populations are particularly interesting. Tibetans, Andeans, and Ethiopian highlanders have all evolved adaptations to high altitude, but the adaptations are different in each case, reflecting different evolutionary histories and different specific solutions to the same general challenge. The Tibetan adaptation involves changes in oxygen processing that allow Tibetans to function effectively at altitude without producing the elevated red blood cell counts that characterize other high-altitude populations. The Andean adaptation involves higher red blood cell counts and various other physiological adjustments. The Ethiopian adaptation involves yet a different set of changes. The fact that 3 different populations have evolved 3 different solutions to the same environmental challenge tells us something interesting about how evolution works. There are multiple possible biological solutions to the problem of high-altitude living, and different populations have arrived at different solutions through their independent evolutionary histories. Beyond the immediate physiological effects, life at altitude has various long-term effects on human biology and demographics. Births at high altitude tend to involve smaller babies than births at lower elevations, possibly reflecting reduced placental function under conditions of lower oxygen availability. Various other health patterns differ between high-altitude and low-altitude populations, with effects that researchers are still working to understand. The relationship between human biology and high-altitude environments is complex and still being mapped out, but it represents one of the most striking examples of how the physical environment can shape human biology over evolutionary timescales. There is one more aspect of the relationship between mountains and weather that I want to bring in before we close this part. The accumulation of snow and ice on mountains plays an enormous role in the water cycles of vast regions. The snowpack that builds up on mountain ranges during the winter functions as a natural reservoir, storing water that gradually releases as the snow melts during the warmer months. The seasonal melt provides water for rivers that originate in mountain regions, supporting agriculture, ecosystems, and human populations far downstream from the mountains themselves. Many of the world's major rivers originate in mountain glaciers and snowfields, including the rivers that supply water to most of South Asia, much of Western North America, large parts of Europe, and substantial regions of South America. The mountain water systems are essential to billions of people who may never see the actual mountains themselves, but whose lives depend on the water that the mountains store and gradually release. The current climate change presents particular challenges for these mountain water systems. As global temperatures rise, mountain glaciers are retreating around the world, with some smaller glaciers having already disappeared entirely, and others projected to be lost within the coming decades. The reduction in glacial ice affects the timing and magnitude of seasonal water releases, with consequences for agriculture, water supply, and ecological systems downstream. The full implications of these changes are still being worked out, but they represent one of the most concrete ways that climate change is affecting human civilizations through its effects on mountain systems. The mountains themselves will continue to stand in their slow geological way, indifferent to the climate changes occurring on their surfaces. But the water systems that depend on mountain glaciers and snowpack are being altered in ways that will affect human populations for generations to come. So as you continue to drift, hold this image in your mind. A high mountain pass, perhaps in the Himalayas, or the Andes, or the Rockies, in the middle of a winter night. The wind howls around the rocky terrain. Snow has accumulated to substantial depths, building up the seasonal reservoir that will gradually release its water in the spring and summer. Far below the pass, in valleys that the mountains shelter and shape, communities of humans are sleeping. The water that will sustain those communities through the dry months of the coming year is being deposited tonight in the form of snow falling on these high terrain, where it will slowly accumulate, compress, and eventually become part of the rivers that flow down to the lowlands. The mountains are doing their work, the work they have been doing for millions of years. capturing moisture from the atmosphere, storing it as ice and snow, gradually releasing it to the lowlands where it sustains the various ecosystems and human communities that depend on it. None of this requires human awareness or attention. It happens automatically as part of the larger climate system that mountains help to produce. Tonight, like every night, the mountains are working. Tonight, like every night, the systems they support continue to function. The relationship between mountains and the lowland regions they sustain is one of the most fundamental aspects of how the planet's climate works, and the contemplation of it on a quiet night like this one is a kind of acknowledgement of the vast natural systems within which all our human concerns are embedded. Tonight, I want to take you into a question that has accompanied human cultures wherever they have lived in proximity to mountains, and that connects the geological and atmospheric realities we have been discussing to something deeper in the human experience. The question concerns why mountains have been understood as sacred across nearly every human culture that has lived in their presence. Because the pattern is genuinely striking. When you survey the religious and spiritual traditions of the world, you find that mountains have been treated as sacred presences in cultures separated by vast distances, with no apparent contact between them, in patterns that suggest something fundamental about how human beings respond to elevated terrain. Let me start with the breadth of this pattern. In ancient Greek religion, Mount Olympus was understood as the dwelling place of the gods, with the highest peak in the country having a specific cosmic role in the religious imagination. In ancient Mesopotamian religion, the ziggurats that dominated city centers were artificial mountains, deliberately constructed to serve the religious functions that natural mountains served in cultures where natural mountains were available. In ancient Egyptian religion, the pyramids were similarly artificial mountains, with their religious significance connected to the cosmological role that mountain forms played in Egyptian thought. In Hindu cosmology, Mount Meru is the cosmic mountain at the center of the universe, with various specific peaks in the Himalayas being identified as physical manifestations of the cosmic mountain. In Tibetan and Mongolian religious traditions, specific mountains have been understood as sacred presences for thousands of years, with elaborate practices developed around their veneration. In ancient Chinese religion, the 5 sacred mountains played central roles in imperial cosmology and continue to be sites of pilgrimage and religious activity today. In Japanese Shinto, Mount Fuji and many other mountains are treated as sacred kami, with associated shrines and pilgrimage traditions. The pattern extends beyond Asia and Europe. In the religious traditions of the indigenous peoples of the Americas, mountains have been understood as sacred across virtually every culture that lived in their presence. The Andean peoples we discussed in an earlier part recognize specific peaks as apus, living beings with their own personalities and powers. The peoples of Mesoamerica venerated specific volcanoes and other prominent mountains, building temples and conducting rituals at their bases. The various indigenous peoples of North America similarly treated specific mountains as sacred, including the Black Hills of the Lakota and other prairie peoples, the various peaks held sacred by the Pueblo peoples of the Southwest, and Mount Shasta and other peaks in the cosmologies of the indigenous peoples of California and the Pacific Northwest. In Africa, Mount Kilimanjaro and other peaks have held religious significance for the peoples who have lived in their shadow. In Australia, specific rock formations and elevated terrain features have been central to Aboriginal religious traditions for tens of thousands of years. The consistency of this pattern across cultures that supposedly developed independently is striking enough to require explanation. Why should mountains be understood as sacred so widely across human cultures? The standard explanations involve several factors that operate together. First, mountains are often the most visually prominent features of the landscape, drawing the eye and the attention of anyone who lives within sight of them. The basic perceptual experience of looking at a mountain produces an immediate impression of magnitude and presence that probably contributes to the religious responses that mountains evoke. Second, mountains often produce dramatic weather phenomena, including storms, lightning, snow, and clouds that wreathe their peaks. These phenomena, observed from below, can give the impression that the mountains are active participants in atmospheric and cosmic events, rather than merely passive features of the landscape. Third, mountains typically contain regions that are difficult or impossible to reach, with the high peaks being inaccessible to ordinary human activity. The unreachable nature of the highest terrain reinforces the sense that the mountains contain spaces that exist beyond the human realm, with their own kinds of presences and activities. But these standard explanations, while they capture part of the picture, may not capture the full depth of why mountains have been treated as sacred so consistently. There is something about the specific character of mountains, the combination of mass and elevation and visual presence and weather-making capability, that seems to resonate with deep features of the human religious imagination in ways that other geographic features do not. Forests can be sacred, rivers can be sacred, particular trees can be sacred, but no other geographic feature has been treated as sacred quite so consistently across cultures as mountains have been. Whatever it is about mountains that produces this response, it appears to be operating at a level deeper than mere cultural convention or coincidental similarity. I want to bring in here something genuinely interesting about the specific kinds of religious experiences that mountains have inspired. Across cultures, mountains have been associated with specific categories of religious practice and experience that recur with notable frequency. Mountains have been sites of revelation, places where individuals or communities have received what they understood as direct communication from divine or supernatural sources. The Hebrew Bible records Moses receiving the Ten Commandments on Mount Sinai. The Greek tradition records various oracular pronouncements at mountain shrines. The Buddhist tradition records the enlightenment of various teachers at mountain retreats. The Japanese tradition records similar experiences at sacred mountains. The pattern of mountains as sites of revelation appears across multiple religious traditions, suggesting that there is something about the experience of being in mountain environments that has been particularly conducive to whatever it is that produces religious revelation. Mountains have also been sites of ascetic practice, places where individuals or groups have withdrawn from ordinary social life to pursue various forms of spiritual discipline. The Christian tradition includes a long history of mountain hermitages, with monks and ascetics establishing themselves in mountain locations to pursue lives of prayer and contemplation. The Buddhist tradition includes similar mountain monasticism, with major monasteries established in mountain regions across Tibet, Nepal, China, Japan, and elsewhere. The Hindu tradition includes various forms of mountain-based ascetic practice, particularly associated with the Himalayas. The Taoist tradition specifically associates spiritual cultivation with retreat to mountain environments, with the relationship between the mountain landscape and the cultivation of spiritual capacities being central to Taoist thought. The cross-cultural pattern of mountains as sites for ascetic withdrawal suggests that mountain environments have been understood as somehow conducive to the development of spiritual capacities that are difficult to cultivate in ordinary social settings. There are practical reasons why mountains might serve these religious functions. The relative isolation of mountain locations provides separation from the distractions of ordinary social life. The harshness of mountain conditions provides natural challenges that ascetic practitioners can work with. The thin air of high elevations may produce altered states of consciousness that have been interpreted as spiritually significant. The visual beauty of mountain landscapes may inspire the contemplative attention that religious practice typically requires. These practical factors probably contribute to why mountains have been chosen as religious sites. But they may not fully explain the specific quality of mountain religiosity, the way that mountains have been understood not just as convenient locations for religious practice, but as themselves participating in religious significance. I want to address something that follows from this. The peoples who have lived in close proximity to specific mountains have typically developed elaborate frameworks for understanding their relationships with those mountains. Frameworks that go far beyond treating the mountains as backdrops for human activity. The relationships are often described in terms of reciprocity, with the mountains providing various forms of support to the human community, and the community in turn maintaining the relationship through various forms of acknowledgement, including offerings, prayers, and ceremonies. The mountains in these frameworks are not just impressive features of the landscape. They are participants in a network of relationships that includes the human community, the various other beings of the local environment, and the larger cosmic order within which everything has its place. This relational understanding of mountains has practical implications that have shaped how peoples have actually lived in mountain environments. Traditional practices typically include various restrictions on what can and cannot be done in mountain regions, with certain peaks being entirely off limits to ordinary human activity, certain areas being reserved for specific religious purposes, and certain resources being treated as belonging to the mountain rather than being available for unrestricted human use. These restrictions, while they have spiritual or religious motivations in their original cultural contexts, often serve practical conservation functions, preserving ecosystems and resources that might otherwise be overexploited. The traditional Andean prohibitions against unrestricted hunting in certain mountain zones, for instance, helped to maintain populations of wildlife in those zones over many generations. The traditional Tibetan practice of designating certain mountains as sacred and off-limits to ordinary use similarly helped to preserve mountain ecosystems. The religious frameworks that treated mountains as sacred had practical consequences that, intentional or not, contributed to the long-term sustainability of human mountain relationships. The arrival of modern industrial civilization has dramatically disrupted these traditional frameworks in many regions. The understanding of mountains as sacred presences with which humans must maintain reciprocal relationships has been replaced, in many contexts, by the understanding of mountains as sources of resources that can be extracted, recreational opportunities that can be commercialized, and obstacles that can be tunneled through or driven over. The shift has had consequences that traditional cultures often warned about, with mountain ecosystems being disrupted, sacred sites being damaged or destroyed, and the relationships between mountain communities and their surrounding environments being fundamentally altered. The modern industrial relationship with mountains is dramatically different from the traditional relationship, and the consequences of this difference are still being worked out. I want to bring in here something that has been quietly underlying this discussion. The reasons that mountains were treated as sacred across so many cultures may include something that the standard rationalist explanations have difficulty capturing. The traditional cultures that developed elaborate relationships with mountains were responding to features of the actual environment that they perceived directly and that informed their cosmological frameworks. They were not making things up arbitrarily. They were perceiving qualities in the mountain environments around them that struck them as religiously significant, and they were developing frameworks within which those qualities could be acknowledged and integrated into ongoing community life. Whether the qualities they perceived were real features of the mountains, or whether they were projections produced by human cognitive responses to dramatic landscapes, is a question that admits of different answers depending on one's broader philosophical commitments. The traditional cultures themselves treated the qualities as real features of the mountains, with the mountains being understood as participants in the cosmic order rather than as inert physical objects. The modern scientific worldview tends to treat the qualities as projections, with the mountains being understood as essentially passive features that have been invested with religious significance by human cognitive processes. The choice between these interpretive frameworks depends on prior commitments that are not themselves fully settled by the available evidence. What I want to suggest, without committing to any specific metaphysical position, is that the human experience of mountains across cultures has consistently included elements that resist reduction to mere visual perception or environmental utility. People living in mountain regions have consistently reported experiences of presence, of awareness, of relationship with the mountains that go beyond what would be expected if the mountains were purely physical features without any deeper significance. These experiences may be products of human cognitive responses to dramatic environments. They may be perceptions of features that exist in the environment, but that we do not fully understand. The honest position is that we do not know definitively what produces these experiences, and the careful contemplation of them is itself one of the genuine pleasures of thinking about mountains carefully. So as you continue to drift, hold this image in your mind: a pilgrimage path in some mountain region of the world, perhaps in Tibet or in the Andes, or in Japan, or in any of the other regions where mountain pilgrimage has been a traditional practice. A small group of pilgrims is making their way along the path in the slow rhythm that pilgrimage requires. They are heading toward a specific peak that has been understood as sacred for many generations. They have prepared for this journey through various forms of practice and purification. They carry with them offerings to be presented at the various shrines they will pass along the way. Their journey will take days or weeks, depending on the specific tradition. The peak rises ahead of them, the same peak that countless previous generations of pilgrims have approached on the same path, with the same general intentions, in the same spirit of careful relationship with the mountain. The pilgrims do not ascend to the summit in most traditions. They circumambulate the peak, or they reach a particular shrine on its slopes, or they perform their rituals at its base. The summit itself remains the domain of the mountain, not to be intruded upon by human ambition. The relationship is being maintained in this generation, as in all the previous generations, through these patient acts of acknowledgement. Tonight, like every night across countless centuries, somewhere in the world, pilgrims are walking similar paths, performing similar acts, maintaining similar relationships with similar peaks. The pattern continues. The mountains stand. The connection between the human community and the sacred mountains is sustained through the small, ongoing acts of countless people who never meet each other, but who all participate in the same general human practice of relating to mountain presences with the respect that their tradition prescribes. The contemplation of this, on a quiet night like this one, is itself a kind of participation in that practice, even if you live far from any mountain that is sacred in any traditional way. Tonight, I want to take you to one of the most striking aspects of mountain environments, and one that connects to questions about life on this planet in ways that are still being worked out by biologists. I want to talk about how living things have managed to colonize the harsh conditions of high elevations and what the patterns of mountain life tell us about the resilience and adaptability of biological systems. Because mountains are, by any reasonable measure, difficult places for life to exist. The thin air, the cold temperatures, the intense ultraviolet radiation, the limited growing seasons, the steep terrain, the rocky soils, all combine to produce conditions that most species cannot tolerate. And yet life has found ways to inhabit even the highest mountain environments, with specialized organisms occupying ecological niches that would be impossible for most life forms. Let me start with something that may surprise you. Some of the highest places on Earth that support life are not what you might expect. The summit of Mount Everest, at nearly 9,000 meters, supports microbial life. Microorganisms have been recovered from rock samples taken at the highest elevations, and these microbes are actively living in conditions that would kill almost any other form of life. They tolerate extreme cold, intense ultraviolet radiation, and atmospheric oxygen pressures, less than a third of what exists at sea level. They survive long periods of dormancy when conditions become too harsh, then resume metabolic activity when conditions improve enough to support it. The exact details of how these microbes manage to survive at such elevations are still being worked out, but their existence demonstrates that life has found ways to inhabit even the most extreme mountain environments, given enough time and evolutionary pressure. Below the realm of pure microbial existence, the highest elevations that support more complex life are typically dominated by lichens. Lichens are symbiotic organisms, formed by partnerships between fungi and algae or cyanobacteria, with the partners contributing different capabilities to produce a composite organism that can survive conditions that neither partner could tolerate alone. The fungal component provides structural support and protection, while the photosynthetic partner provides the food production through photosynthesis. Lichens can be found on rocks at elevations up to about 7,000 meters, where they form the highest visible communities of multicellular life on the planet. The growth rates of these high-altitude lichens are extraordinarily slow, sometimes measured in fractions of a millimeter per year, which means that the lichens visible on high mountain rocks today have often been growing for centuries or millennia. The patches of lichen that visitors can see on rocks at the bases of glaciers and in other high mountain environments may be older than many human civilizations, having grown patiently in their specific spots for hundreds of generations of human history. Above the lichen zone, but below the limits of vascular plant growth, mountain environments often support a category of plants called cushion plants. These are low-growing perennials that have evolved to form dense, compact mounds, with all their leaves and stems packed tightly together close to the ground. The cushion form provides several adaptive advantages in high-altitude conditions. The dense packing creates a microclimate within the cushion itself, with temperatures, humidity, and wind exposure all moderated relative to the surrounding environment. The low profile reduces wind exposure and heat loss. The substantial root systems that cushion plants typically develop allow them to access water and nutrients from a relatively large volume of soil. The result is a plant form that can survive conditions that would kill most other plants, growing slowly but persistently in environments that appear at first glance to be entirely hostile to plant life. The flowers that cushion plants produce when they bloom are often spectacularly beautiful, with bright colors and substantial size relative to the overall plant. The contrast between the harsh, barren, rocky environment and the small, intense flowers can be striking, and it has impressed visitors to high mountain regions for as long as humans have been climbing into these zones. The flowers serve specific reproductive functions, attracting the limited pollinators that can survive at high elevations, but they also provide one of the genuine aesthetic experiences available in the alpine zone. Anyone who has spent time above the tree line in mountain regions has probably encountered cushion plants in flower, and the experience tends to be memorable. The animals that inhabit high mountain environments have developed their own remarkable adaptations to the conditions. The animals of the high mountains face many of the same challenges that the plants face, including reduced oxygen, extreme temperatures, intense ultraviolet radiation, and limited food availability. The specific adaptations vary across species, but several patterns recur. Many high-altitude animals have developed enhanced oxygen utilization capabilities, with various adjustments to their respiratory and circulatory systems that allow them to function at oxygen pressures that would impair lowland animals. Many have developed specialized fur or feather coats that provide insulation against extreme cold. Many have evolved specific behavioral patterns that allow them to seek shelter during the harshest conditions while remaining active during periods when conditions are more tolerable. The cumulative result is a set of animal species that can thrive in environments where most species cannot survive at all. Some of the most striking examples of high-altitude animal adaptation are found among the mammals. The yak, native to the Tibetan Plateau and the Himalayan region, can live at elevations up to about 6,000 meters, far above where most mammals can exist. Yaks have evolved larger hearts and lungs relative to their body size than their lowland cattle relatives, along with specific genetic adaptations to oxygen utilization that allow them to function at the elevations where they live. They are essential to the human cultures of the high Himalayan region, providing transport, milk, meat, fiber, and various other resources that have allowed human populations to inhabit these elevations for thousands of years. The relationship between Tibetan and Himalayan peoples and their yaks is one of the most extensive examples of human-animal interdependence at high altitudes, with both species being dependent on each other for survival in environments that would be impossible for either to inhabit alone. The Andean equivalent of the yak is the llama and its wild relatives the vicuña and guanaco. These South American camelids have evolved their own adaptations to high-altitude life, including specialized hemoglobin that has higher oxygen affinity than the hemoglobin of their lowland relatives. The vicuña, in particular, can survive at elevations up to about 5,500 meters on the high altiplano grasslands of the Andes. Like the yak in the Himalayan region, the camelids of the Andes have been essential to the human civilizations of the high mountain region, providing the foundation for the agricultural and pastoral economies that supported the various pre-Columbian cultures we discussed in earlier parts of this exploration. The Inca Empire, in particular, depended heavily on llamas and alpacas for transport, fiber, and various other resources, and the relationships between humans and these animals continue in modified forms in modern Andean communities. The birds of high mountain environments include some of the most impressive flying species on the planet. The Andean condor, with its 3-meter wingspan, is one of the largest flying birds and can soar at elevations up to about 6,000 meters with apparent ease. The bar-headed goose, native to Central Asia, regularly migrates over the Himalayas, flying at elevations of 7,000 meters or more during its journeys between summer breeding grounds in Central Asia and winter habitats in the Indian subcontinent. The bar-headed goose has evolved specific genetic adaptations that allow it to extract oxygen from the thin air at altitude with remarkable efficiency, making it one of the most physiologically extreme birds on the planet. The fact that these large birds can fly at elevations where humans cannot survive without supplemental oxygen demonstrates how dramatically biological adaptation can extend the range of conditions that organisms can tolerate. I want to bring in something that I find genuinely interesting about high-altitude ecosystems. The species that live in these environments often have unusually long lifespans relative to their body sizes, and they often grow and reproduce more slowly than their lowland relatives. The bristlecone pine, a tree species native to the high mountains of the western United States, can live for thousands of years, with the oldest known individual being more than 4,800 years old. The slow growth rates of these trees, with annual growth rings sometimes measuring less than a millimeter, mean that the trees accumulate substantial age while remaining relatively small in size. The patient persistence of these ancient trees has produced individuals that have been alive longer than most human civilizations, witnessing centuries of human history while standing silently in their high mountain locations. The oldest bristlecone pines were already mature trees when the pyramids of Egypt were being built, and they continue to live today in the same locations where they have stood for nearly 5 millennia. The bristlecone pines tell us something important about the relationship between environmental harshness and biological longevity. Counterintuitively, the harshest environments often produce the longest-lived organisms. The slow growth rates that mountain conditions impose mean that the organisms accumulate damage less rapidly, and they invest in maintenance and repair rather than rapid reproduction. The same patterns occur in various other high-altitude species, with the harsh conditions of mountain environments producing organisms that live slowly but persistently across very long periods. The mountains are, in this sense, repositories of biological time, with the species they support, including some of the oldest individual organisms on the planet. The relationship between high-altitude life and the cycles of geological and climatic change deserves attention. The species that currently inhabit high mountain environments arrived at their current elevations through complex evolutionary histories that involved repeated movements as climate conditions changed. During the ice ages, when global temperatures were lower, many high-altitude species were able to expand into lower elevations, as the cooler climate made these elevations more suitable for their requirements. During warmer periods, the same species retreated to higher elevations as the lowlands became too warm for them. The current high-altitude communities are products of these repeated movements, with the specific compositions of mountain ecosystems reflecting the climatic histories of the regions in which they exist. This pattern has implications for the current period of climate change. As global temperatures rise, the species that currently inhabit high-altitude environments are being pushed toward even higher elevations, with the lower limits of their habitable zones moving upward. For species that are already near the limits of their thermal tolerance, this upward movement may eventually run out of room. The summit of even the highest mountain provides only so much vertical space, and species that are already near the top have nowhere to go if conditions continue to warm. Various researchers have begun documenting upward shifts in mountain species distributions in response to recent climate change, and the projections for the coming decades suggest substantial losses of high-altitude biodiversity if current warming trends continue. The mountains will continue to stand, but the specific assemblages of species that currently inhabit them are vulnerable to the climate changes that are unfolding around them. There is one more aspect of mountain biology I want to address before we close this part. The isolation of mountain environments has produced patterns of biological diversification that are particularly striking. Different mountain ranges, even those that are relatively close to each other, often support distinctive species that occur nowhere else, having evolved in isolation from related populations on other mountains. The high mountain ranges of East Africa, for instance, support distinctive species of plants and animals that occur on individual mountains, but not on neighboring ones, despite the mountains being separated by relatively short distances. The same pattern occurs in the Andes, in the Himalayan region, and in many other mountain systems. The mountains function as biological islands, with their isolated peaks supporting evolutionary processes that produce species found nowhere else. The biodiversity of mountain regions is therefore often substantially higher than the biodiversity of the surrounding lowlands, with the patchwork of isolated mountain ecosystems supporting many endemic species that contribute disproportionately to global biodiversity. So as you continue to drift, hold this image in your mind. A high alpine meadow in late summer, perhaps in the Rocky Mountains or the Alps or the Himalayan foothills, in the middle of the night. The grasses and small flowering plants that fill the meadow are mostly dormant in the cool darkness. A pika, one of the small rabbit-like mammals that inhabit high mountain environments, is sheltering in its burrow under a pile of rocks. An ancient lichen patch covers a rock face nearby, having grown patiently in this exact spot for centuries. Higher up the slope, a cushion plant occupies a small patch of soil, with all its leaves and stems pulled close to the ground in the configuration that has allowed plants of its kind to survive in this environment for thousands of generations. Higher still, in elevations where almost nothing visible lives, microorganisms continue their slow metabolic activity in tiny pockets of habitable conditions. The whole vertical sequence of life zones, from the relatively rich meadow to the nearly sterile high peaks, exists tonight as it has existed for many human generations, with each zone occupied by the specific organisms that have evolved to thrive in its specific conditions. Tomorrow, the sun will rise and the activity of the day will resume. The pikas will emerge to gather food. The pollinators will return to the alpine flowers. The lichens will continue their imperceptibly slow growth. The mountains will continue to provide the specific conditions that this whole community of life requires. The system will continue, as it has continued, through countless nights and countless days, for as long as the mountains have stood at their current elevations. Tonight, like every night, the high mountain world is doing its work, in patterns that no individual human will ever fully observe, but that have been continuing in essentially their current form for thousands of years.